What if I told you the universe is caught in an endless struggle, a silent battle between two invisible giants that dictate the fate of everything? On one side, gravity, the force that binds galaxies together, pulling stars into majestic spirals and holding planets in their orbits. On the other, dark energy, the mysterious presence pushing the cosmos apart at an ever-increasing speed, stretching the fabric of space itself. This isn't science fiction. It's the reality of our universe, and the stakes couldn't be higher, because right now, these two titans are locked in a cosmic tug of war, and the outcome will determine whether the universe ends in a fiery collapse or fades into cold, endless darkness. But here's where it gets even more fascinating. For decades, scientists believed this battle followed predictable rules until now. Enter the 38 cosmic balances, a revolutionary set of theories that could rewrite everything we thought we knew about dark energy and gravity. These ideas don't just tweak the equations, they flip the script entirely, suggesting hidden harmonies and unseen forces at play. Imagine discovering that the universe isn't just expanding, it's dancing to rhythms we never noticed, balancing on a knife's edge between creation and destruction. That's the power of these new theories. They don't just explain the universe, they reveal its hidden poetry. So what does this mean for us? Why should we care about a war happening billions of light years away? Because this isn't just about distant galaxies or abstract physics. It's about understanding the very framework of reality, why we exist, how our world came to be, and what lies ahead for the cosmos. Whether you're a casual stargazer or a die-hard science enthusiast, these discoveries will change how you see the night sky, because once you glimpse the delicate balances holding the universe together, you'll never look at the stars the same way again. So let's dive in, because the greatest show in the cosmos is about to begin, and you've got a front row seat. Picture the universe as a grand stage where two cosmic actors perform an eternal duet, one pulling, the other pushing, neither ever yielding completely. Dark energy, that enigmatic force stretching space itself, isn't just some invisible backdrop. It's an active player, accelerating galaxies away from each other like an unstoppable tide. Meanwhile, gravity works tirelessly in the opposite direction, weaving matter into galaxies, stars, and planets with its relentless grip. For years, scientists assumed this was a winner-takes-all fight, a showdown where one force would eventually crush the other. But the 38 cosmic balances turn that idea on its head. They reveal something far more intriguing. This isn't a battle at all, it's a collaboration. Think of it like a cosmic seesaw. On one end, dark energy flings galaxies apart. On the other, gravity pulls them into clusters and superclusters. The magic happens in the middle, where these forces don't cancel each other out but instead find a precarious harmony. This balance isn't static, though. It shifts over billions of years, adjusting like a thermostat to keep the universe from tearing itself apart or collapsing inward. Without this delicate dance, galaxies might never have formed in the first place. Too much dark energy early on, and matter would have scattered too widely to clump together. Too much gravity, and the universe might have collapsed back in on itself before stars could even ignite. Here's where it gets even wilder. These balances aren't random. They follow precise mathematical relationships, almost as if the universe has built-in rules to prevent either force from gaining total control. Some researchers compare it to a symphony, where dark energy and gravity are instruments playing in counterpoint, each with its own melody, yet together creating something greater. This could explain why we live in such a Goldilocks cosmos. Not too fast, not too slow, but just right for complexity and life to emerge. What does this mean for the future? If these theories hold, the universe might avoid the dramatic endings we once feared. No catastrophic big crunch where everything collapses. No lonely big freeze where galaxies vanish into darkness. Instead, the cosmic balances suggest a middle path, a universe that continues evolving, adjusting, and perhaps even recycling itself in ways we're only beginning to imagine. So the next time you look up at the night sky, remember, you're not just seeing stars, you're witnessing the universe's greatest balancing act, a performance billions of years in the making, and it's far from over. The story of gravity began with something seemingly simple, an apple falling from a tree. When Isaac Newton described this force in the late 1600s, he gave us the first mathematical rules of attraction, showing how the same pull that brought fruit to the ground also kept the moon in orbit around Earth. It was a revelation, a way to quantify the invisible threads connecting all matter in the cosmos. But Newton's gravity had limits. It couldn't explain everything, like the peculiar wobble in Mercury's orbit or the way light bent around massive objects. That's where Albert Einstein stepped in. His theory of general relativity, published in 1915, reimagined gravity not as a force, but as the curvature of spacetime itself. Massive objects like stars and planets didn't just pull on each other. They warped the very fabric of the universe, creating the effects we perceive as gravity. For decades, Einstein's equations seemed flawless. They predicted black holes, gravitational waves, even the expansion of the universe, all later confirmed by observation. But there was a twist. When Einstein first applied his equations to the cosmos, they suggested the universe should either be expanding or contracting. At the time, astronomers believed it was static, so Einstein added a fudge factor, a cosmological constant, to balance things out. Later, when Edwin Hubble discovered the universe was indeed expanding, Einstein called this constant his greatest blunder. Little did he know that same idea would make a dramatic comeback nearly a century later. The real shock came in 1998. Two teams of astronomers studying distant supernova made a discovery that turned cosmology upside down. Instead of slowing down as expected, the universe's expansion was speeding up. Something was pushing galaxies apart faster and faster, an anti-gravity force we now call dark energy. Suddenly, Einstein's blunder didn't seem so foolish. His cosmological constant, or something like it, might be real after all. This is where the 38 cosmic balances enter the picture. They don't just build on this history, they weave it into something entirely new. By revisiting Newton's equations, Einstein's relativity, and the puzzles of dark energy, these theories suggest hidden connections between forces we thought were separate. Imagine gravity and dark energy not as rivals, but as two sides of the same cosmic coin, each adjusting to the other in a precise, almost choreographed interplay. It's as if the universe has been following a secret set of rules all along, rules that ensure stability across billions of years. What's truly remarkable is how these ideas bridge the old and the new. Newton gave us the language of forces. Einstein revealed the geometry of spacetime. Dark energy forced us to confront the unknown. Now, the cosmic balances propose a framework where all these pieces fit together, not as contradictions, but as chapters in a much larger story. And if they're right, we might finally be on the verge of understanding why the universe behaves the way it does. Not as a battleground, but as a stage where every force plays its part in perfect, if mysterious, harmony. The 38 cosmic balances aren't just a single idea, they're a symphony of principles, each playing a distinct role in shaping the universe. Imagine them as invisible dials fine-tuning reality itself, adjusting the tension between dark energy and gravity at every scale. Some balances work on the grand stage of galactic superclusters, ensuring these colossal structures don't fly apart or collapse inward. Others operate in the vast, empty voids between galaxies, where dark energy's push is strongest, subtly regulating how fast those voids grow. Then there are balances that govern smaller cosmic neighborhoods, like the way stars cluster or how planets hold their orbits. Together, they form a delicate web of interactions, each one maintaining equilibrium in ways we're only beginning to decode. Take the fifth balance, for instance, often called the filament rule. It explains why galaxies aren't scattered randomly but instead form intricate, thread-like structures spanning billions of light years. Without this balance, gravity would clump matter into chaotic knots, or dark energy would tear these filaments apart before they could form. Another striking example is the 12th balance, which dictates how fast cosmic voids expand. These voids aren't just empty space, they're dynamic regions where dark energy's influence is most visible. The 12th balance ensures they grow at just the right rate, preventing the universe from becoming a patchwork of overcrowded clusters and barren deserts. What's truly groundbreaking is how these balances interconnect. They don't operate in isolation. They're part of a larger cosmic feedback loop. The same forces that shape a single galaxy also influence the universe's ultimate fate. For example, the 23rd balance links the density of dark matter in a galaxy to the local strength of dark energy, almost as if the universe has a built-in thermostat adjusting the two forces in real time. This could explain why some galaxies age gracefully, while others burn out too soon. And then there's the most mysterious balance of all, the 38th. Unlike the others, it doesn't govern a specific structure or region. Instead, it acts as a cosmic wildcard, a kind of failsafe that kicks in when other balances are strained. Some theorists speculate it's the universe's way of correcting itself, a hidden mechanism that prevents runaway expansion or collapse. If true, it would mean the cosmos has a built-in resilience we never anticipated, a safety net woven into the fabric of spacetime. This framework doesn't just explain what we see, it reshapes how we think about cosmic evolution. Suddenly, phenomena that seemed unrelated, like the way black holes anchor galaxies, or why certain stars explode with precise brightness, start to fit together. The balances suggest a universe that's far more interconnected than we imagined, where every action, from the birth of a star to the motion of a galaxy, is part of a grander equation. And if we can decode even a fraction of these principles, we might finally answer the biggest question of all. Is this delicate equilibrium accidental, or is it the signature of something deeper? The first cosmic balance is like the universe's master tuning knob, a precise setting that determines whether everything holds together or flies apart. It's called the critical density threshold, and it's the reason the cosmos hasn't already torn itself to shreds or collapsed into a black hole. Picture this ratio as a cosmic tightrope walker. One side is matter, with its gravity pulling inward. The other is dark energy pushing outward. If the balance tipped even a fraction toward matter, gravity would dominate, yanking galaxies into chaotic collisions until the universe crumpled in on itself. Tilt the other way, and dark energy would accelerate expansion so violently that stars, planets, and even atoms would be ripped apart before life could ever form. Yet here we are, in a universe where this ratio sits perfectly in the Goldilocks zone. The numbers are staggering. Dark energy makes up roughly 68% of the universe's total energy density, while matter accounts for about 27%, with ordinary matter, the stuff of stars and planets, comprising less than 5% of that. The remaining 5%, that's where things get even more intriguing. It's a margin so slim, so precise that it feels less like luck and more like a cosmic blueprint. Some researchers argue this isn't random at all. They point to the fact that if dark energy were just slightly stronger, galaxies would never have clumped together in the first place. Slightly weaker, and the universe might have collapsed before the first stars ignited. This balance doesn't just explain the universe's structure, it raises profound questions about why these values are what they are. Could there be an undiscovered law of physics locking this ratio in place? Or is our universe one of many, each with different settings, and we just happen to live in the one where the numbers allowed life to emerge? The critical density threshold isn't just a curiosity, it's a window into the deepest mysteries of existence. It challenges us to ask whether the universe is built on accidents or architecture, and whether we're here by chance or by design. And here's the kicker, this balance isn't static. Over billions of years, as the universe expands and dark energy's influence grows, the ratio shifts. That means the delicate equilibrium we see today is a snapshot of a dynamic process, one that's been adjusting since the Big Bang. It's as if the universe is constantly recalibrating itself, ensuring stability across eons. So when you look up at the night sky, remember, every star, every galaxy, every atom in your body exists because of this razor-thin margin, a cosmic tightrope walk spanning 14 billion years with no safety net in sight. The second cosmic balance reveals something astonishing. The universe isn't just expanding. It's expanding at exactly the right speed to build galaxies without tearing them apart. Imagine a master architect designing a bridge that stretches while it's being built, its materials strengthening just fast enough to keep pace with the widening gap. That's the expansion-structure trade-off in action. On one side, dark energy relentlessly stretches the fabric of space, pushing galaxies apart like dots on an inflating balloon. On the other, gravity fights back, pulling matter into galaxies, clusters, and the vast cosmic web we see today. The miracle isn't that these forces oppose each other, it's that their opposition is perfectly matched, like two dancers whose every move cancels the others in flawless harmony. Let's break down why this balance is so extraordinary. If dark energy were even slightly stronger, its push would have overwhelmed gravity in the universe's infancy. Gas clouds would never have collapsed to form stars. Galaxies would have evaporated before they could take shape. The cosmos would be a lonely sea of scattered particles, forever drifting apart. But if gravity had dominated, the story would be equally bleak. Matter would have clumped together too quickly, triggering a catastrophic collapse, a big crunch before life could even begin. Instead, we exist in a universe where the expansion rate is fine-tuned to the exact precision needed for structure to emerge. Stars ignite, galaxies spiral. Planets coalesce in the quiet pockets between these titanic forces. The numbers behind this are mind-bending. Measurements show the universe's expansion rate. The Hubble constant hovers around 70 kilometers per second per megaparsec. That means for every 3 million light-years you look deeper into space, galaxies recede 70 kilometers faster each second. But here's the catch, this rate isn't constant over time. In the early universe, gravity briefly had the upper hand, allowing matter to cluster. Then, around 5 billion years ago, dark energy turned on, accelerating expansion just as large-scale structures were mature enough to resist being torn apart. This timing isn't coincidental. It's baked into the 38 balances as a fundamental rule, a cosmic algorithm ensuring structure formation and expansion evolve in lockstep. What's even wilder, this balance isn't uniform. In dense galaxy clusters, gravity's grip is strong enough to locally resist dark energy's pull, creating stable islands in the expanding cosmos. Meanwhile, in the vast voids between galaxies, dark energy reigns supreme, stretching space faster than gravity can counteract. The 38 balances account for these regional differences, describing how the universe self-regulates like a grand ecosystem. It's not a single, rigid equation but a dynamic interplay, adjusting itself across scales and epochs to preserve the conditions for complexity and life. So the next time you gaze at the Milky Way's shimmering band, remember, you're not just seeing stars, you're witnessing a cosmic tightrope walk 14 billion years in the making, where the slightest misstep would have left the universe barren. Yet here we are, in a Goldilocks cosmos where the push and pull of invisible forces conspire to make existence possible. That's the quiet brilliance of the second balance, not just explaining how the universe works, but revealing how astonishingly fine-tuned it had to be for us to notice it at all. The third cosmic balance unveils the universe's hidden scaffolding, a delicate equilibrium between vast, empty voids and the glittering filaments of galaxies that thread through them. Picture the cosmos as a sponge, with galaxies clinging to its intricate, web-like structure while the gaps between them stretch into unimaginable emptiness. These voids aren't just blank spaces, they're dynamic regions where dark energy flexes its power, pushing boundaries outward like an unstoppable tide. Meanwhile, gravity works in the denser filaments, pulling matter into shimmering ribbons of stars and gas. What's astonishing isn't just that these forces oppose each other, it's how perfectly they compensate, creating a universe where emptiness and abundance exist in precise, harmonious tension. Consider the Boots void, one of the largest known cosmic voids, spanning over 300 million light-years. It's so vast that if our Milky Way sat at its center, we wouldn't have discovered other galaxies until the 1960s. Yet this emptiness isn't accidental. Dark energy has sculpted it, accelerating its expansion over billions of years. Now, turn your gaze to the nearby Hercules Corona Borealis Great Wall, a filament of galaxies so massive it challenges our understanding of cosmic scale. These extremes, voids and filaments, aren't random. They're two sides of the same cosmic equation, their sizes and distribution locked into balance by the universe's hidden rules. The 38 balances reveal how this equilibrium works. Too much dark energy, and voids would grow so quickly they'd rip filaments apart before galaxies could form. Too much gravity, and matter would collapse into dense knots, leaving no room for the vast voids that define the cosmic web. Instead, the third balance acts like a universal regulator, adjusting the expansion of voids and the density of filaments in real time. It's why we see galaxies clustered along delicate threads, with voids occupying roughly 80% of the universe's volume, a ratio so consistent across space that it can't be coincidence. Here's where it gets even more fascinating. This balance isn't static. Early in the universe's history, gravity dominated, pulling matter into the first filaments. As dark energy's influence grew, voids began expanding, but at a rate calibrated to preserve the filamentary structure. The result, a cosmos where voids grow just fast enough to stretch the cosmic web without snapping it. Some theorists compare it to a symphony conductor, ensuring the string's filaments and the pause's voids create a harmonious whole. Without this equilibrium, the universe would be unrecognizable. A dark energy-dominated cosmos would be a lonely, featureless expanse. A gravity-dominated one would resemble a cosmic avalanche, a chaotic jumble of matter collapsing in on itself. Instead, we inhabit a Goldilocks universe where emptiness and abundance coexist, each defining the other. It's a reminder that the cosmos isn't just a collection of objects, but a dynamic interplay of forces, and we're here because against all odds, those forces found perfect balance. At the heart of nearly every galaxy lurks a supermassive black hole, not just a silent destroyer, but an unexpected architect of cosmic balance. The fourth cosmic balance reveals these gravitational monsters as active regulators in the dark energy gravity war, emitting energy that stabilizes their surroundings like cosmic pressure valves. Picture a black hole not as a vacuum cleaner sucking everything in, but as a dynamic engine. As it devours gas and stars, it doesn't just consume, it radiates. Jets of energy scream outward at nearly light speed, heating surrounding gas so intensely that it can't collapse further under gravity's pull. This creates a feedback loop. The more material a black hole eats, the more energy it blasts back out, preventing runaway collapse in the galaxy's core. It's nature's way of hitting the brakes before gravity spirals out of control. Now here's where it gets revolutionary. Recent observations suggest these black holes might do more than just stabilize. They could be covert producers of dark energy itself. When astronomers studied supermassive black holes across cosmic time, they found something bizarre. These objects grow larger than expected, as if drawing energy from an unseen source. One radical theory proposes that black holes contain vacuum energy, the same fundamental force driving the universe's expansion. Instead of just warping space with gravity, they might also stretch it from within, acting as local fountains of dark energy. Imagine billions of these cosmic taps scattered across the universe, each subtly tweaking the balance between attraction and repulsion. This changes everything we thought we knew about galactic evolution. Take the Milky Way's own Sagittarius, a star. For years, its quiet demeanor puzzled scientists. Why isn't it devouring more of our galaxy? The answer might lie in the fourth balance. As Sagittarius, a star, feeds, its energy emissions push back against incoming gas, creating a self-regulating diet. Too much food, it fires up its jets and blows the excess away. Too little, it quiets down, waiting for the next cosmic snack. This dance isn't unique to our galaxy. From Andromeda's raging core to the faintest dwarf galaxies, black holes seem to adjust their appetite to maintain equilibrium, like invisible conductors keeping the galactic orchestra in tune. The implications stretch far beyond individual galaxies. If black holes truly contribute to dark energy, their collective influence could explain why the universe's expansion accelerates. Each one, from the smallest to the most massive, might be a microscopic engine of cosmic expansion, their combined output shaping the fate of everything. It's a staggering thought that the darkest objects in existence could secretly be fueling the very force that pushes the universe apart. And if this balance holds, it would mean black holes aren't just in points of gravity's victory, but essential players in the universe's grand equilibrium, destroyers and creators all at once. Deep in the fabric of reality, where space and time become fuzzy, something extraordinary happens. Empty space isn't really empty, it's a seething ocean of quantum particles popping in and out of existence like bubbles in a boiling pot. These fleeting fluctuations should, by all rights, warp space-time into chaos, creating microscopic ripples that amplify into cosmic-scale distortions. Yet when we look out at the universe, we see something baffling. On large scales, space-time is eerily smooth, like a perfectly still pond. The fifth cosmic balance holds the key to this mystery, a delicate truce between the frenetic energy of quantum foam and gravity's power to smooth out the wrinkles. Think of it like a cosmic tug of war where both sides are equally matched. On one end, quantum fluctuations generate unpredictable spikes of energy, twisting space-time at the smallest scales. On the other, gravity acts like an invisible hand, stretching and smoothing those distortions before they can escalate. The balance between them isn't random. It's precise enough to prevent the universe from tearing itself apart at the seams or collapsing into a knot of tangled spacetime. Without this equilibrium, galaxies might never have formed, and light could have traveled in erratic, broken paths across the cosmos. Instead, we inhabit a universe where the chaos of the quantum realm stays contained, allowing structure to emerge on grand scales. This balance becomes even more astonishing when you consider the numbers. Quantum fluctuations generate energy densities trillions of times stronger than what we observe in the universe's expansion. If these micro-explosions weren't perfectly counteracted by gravity's smoothing effect, space-time would resemble a stormy sea rather than the calm expanse we see today. Some researchers suggest this isn't just coincidence, it's evidence of a deeper symmetry woven into the laws of physics, one that keeps the universe stable across all scales. Here's where the fifth balance gets truly mind-bending. It might also explain one of cosmology's biggest puzzles, why the early universe was so uniform. The cosmic microwave background, the afterglow of the Big Bang, shows temperature variations of just 1 part in 100,000, meaning matter was distributed with near-perfect smoothness. That shouldn't be possible if quantum fluctuations were left unchecked. Yet if the fifth balance was active even in those first moments, it could have acted as a cosmic filter, letting gravity iron out the wrinkles before they could grow. Now imagine this balance failing just for an instant. A slight tilt toward quantum chaos, and space-time might have fractured into unstable pockets, some expanding uncontrollably while others collapsed. A tilt toward gravity's dominance, and the universe could have become too rigid, preventing the formation of stars and galaxies. Instead, we exist in a reality where these forces hold each other in perfect check, creating the conditions for everything we know. It's a reminder that the universe's stability isn't guaranteed. It's the result of countless invisible negotiations happening every moment on scales we're only beginning to comprehend. Dark matter might be invisible, but it's the universe's silent negotiator, a cosmic peacekeeper ensuring galaxies don't tear themselves apart or collapse under their own weight. Picture a spiderweb glistening with dew, each strand perfectly tensioned to hold its shape. Dark matter does the same for galaxies, its gravitational pull weaving an unseen scaffold that offsets dark energy's relentless push. This sixth cosmic balance reveals something extraordinary. Dark matter isn't just a passive bystander. It's an active mediator, fine-tuning gravity's grip to match the expansion force of dark energy with near mathematical precision. Take our own Milky Way as an example. Visible stars and gas clouds account for less than 10% of the galaxy's total mass. The rest, a vast, invisible halo of dark matter, stretching far beyond the galaxy's luminous edges. Without this hidden anchor, the Milky Way's outer stars would fling outward like sparks from a spinning firework, unable to resist dark energy's cosmic tide. Yet they don't. Instead, they orbit at speeds that defy conventional physics unless you factor in dark matter's gravitational influence. This isn't unique to our galaxy. From the smallest dwarfs to the largest spirals, dark matter's distribution follows a universal blueprint, one that keeps rotations stable and structures intact across billions of years. The numbers behind this balance are staggering. For every particle of visible matter, there's roughly 5 times as much dark matter, a ratio so consistent across galaxies that it can't be accidental. Some researchers argue this isn't just a random quirk of nature. It's a built-in failsafe, a way for the universe to ensure gravity and dark energy never tip too far out of sync. Too much dark matter and galaxies would crush inward, forming dense knots that stifle star formation. Too little, and dark energy would scatter stars like leaves in a hurricane. Instead, we find a Goldilocks arrangement, where dark matter's gravitational scaffolding is precisely calibrated to resist expansion without stifling it entirely. Here's where the sixth balance gets even more intriguing. Dark matter doesn't just offset dark energy, it adapts to it. In regions where dark energy's push is strongest, like the voids between galaxies, dark matter's halo thins out, allowing expansion to proceed unimpeded. Near galaxy clusters where gravity's pull is fierce, dark matter concentrates, creating gravitational anchors that keep entire superclusters from flying apart. This dynamic adjustment isn't random. It follows patterns embedded in the 38 balances, almost as if the universe has a hidden playbook for maintaining equilibrium. What does this mean for the cosmos? Without dark matter's mediating role, galaxies might never have formed in the first place. In the early universe, ordinary matter was too diffused to collapse under its own gravity. Dark matter's extra gravitational pull provided the necessary nudge, gathering gas and dust into the seeds of future galaxies. Even now, it continues to shape cosmic evolution, acting as a counterweight to dark energy's accelerating push. Some theorists go further, suggesting dark matter might even influence dark energy itself, a two-way interaction we're only beginning to explore. So the next time you look at a spiral galaxy's graceful arms or a distant cluster's shimmering halo, remember, what you're seeing is just the tip of the cosmic iceberg. Beneath the visible beauty lies an invisible architecture, a delicate dance of forces orchestrated by dark matter. It's the universe's ultimate mediator, ensuring that gravity and dark energy don't wage war, but work together to build the galaxies, stars, and planets that make our existence possible. Astronomers have been locked in a quiet but fierce debate over one fundamental question: just how fast is the universe expanding? This isn't just academic quibbling. The answer defines the age, size, and ultimate fate of everything we know. For years, two methods of measuring this expansion, observing near-by supernova versus analyzing the cosmic microwave background, kept giving different results. The discrepancy became so persistent they gave it a name: the Hubble Tension. It's as if the universe itself is whispering two different stories, leaving scientists scrambling to figure out why. But the seventh cosmic balance might hold the key. What if dark energy isn't uniform? What if its strength ebbs and flows subtly across the cosmos, creating pockets where space stretches faster or slower than we expect? This idea turns conventional wisdom on its head. We've long assumed dark energy behaves like a constant force, evenly stretching every corner of the universe at the same relentless pace. But imagine dark energy as wind over an ocean, sometimes gusting, sometimes calm, shaping the waves of space-time in unpredictable ways. In regions where it's stronger, galaxies would race apart faster. Where it weakens, gravity gains a slight edge, slowing expansion just enough to throw off our measurements. Suddenly, the Hubble tension isn't a contradiction, it's a clue. Those conflicting results might simply be snapshots of different cosmic neighborhoods, each with its own unique rhythm of growth. Evidence for this is already emerging. Recent galaxy surveys reveal strange variations in expansion rates depending on where you look. Some superclusters seem to drift apart faster than models predict, while voids expand more sluggishly. Even more telling, the cosmic microwave background, the afterglow of the Big Bang, shows faint irregularities that could hint at dark energy's patchy influence. These anomalies fit eerily well with the seventh balance, which proposes that dark energy's strength isn't locked in place, but adjusts dynamically based on the density of surrounding matter. Here's where it gets revolutionary. If this balance holds, it could solve more than just the Hubble tension. It might explain why some galaxies age differently than others, or why certain regions of space seem oddly devoid of young stars. Dark energy's variability would act like a cosmic zoning law, quietly shaping where and how structures evolve. Picture a universe where expansion isn't a single, relentless tide but a mosaic of currents, some rushing, some meandering, all weaving together into the grand tapestry we observe. The implications are staggering. A one-size-fits-all model of cosmic expansion would give way to something far richer, a universe where dark energy and gravity negotiate locally, striking different bargains in different corners of space. It's a vision of reality that's not just balanced but nuanced, where the rules bend ever so slightly from place to place. And if we can map these variations, we might finally unlock the true story of how the universe grows, not as a single narrative, but as countless interwoven tales of push and pull, each revealing a new layer of cosmic harmony. The eighth cosmic balance pulls back the curtain on one of the universe's most astonishing symmetries, a hidden link between the explosive birth of the cosmos and its quiet, accelerating death. Picture the Big Bang not as a single, fleeting event, but as the first note in an eternal symphony. In the tiniest fraction of a second after creation, space itself ballooned outward at unimaginable speed, a process called inflation that stretched the infant universe from subatomic to cosmic scales in less time than it takes light to cross a single proton. That violent expansion left behind faint fingerprints, ripples in spacetime etched into the fabric of reality. Now, here's the staggering part. Those ancient imprints might hold the blueprint for how dark energy operates today, as if the universe is echoing its own explosive beginning in slow motion. This isn't just poetic coincidence. The math reveals eerie parallels. Inflation was driven by a mysterious repulsive force, a kind of primordial dark energy that briefly overpowered gravity, smoothing the cosmos into near-perfect uniformity. Billions of years later, dark energy reawakens, mimicking inflation's playbook by stretching space at an accelerating pace. The eighth balance proposes these aren't separate phenomena, but two phases of a single cosmic cycle. Imagine a pendulum swinging between epochs of rapid expansion and relative calm, with dark energy today acting as inflation's distant, quieter cousin. Evidence for this hides in the cosmic microwave background, the afterglow of the Big Bang, those faint temperature variations mapped with exquisite precision by telescopes like Planck aren't random noise. They're the stretched-out remnants of quantum fluctuations from the inflationary era, frozen in time like footprints in cooling lava. What's mind-blowing is how closely their statistical patterns resemble the large-scale structure of today's universe, the distribution of galaxies, clusters, and voids. It's as if the universe remembered its explosive youth and arranged its adult form as a subtle homage. The implications rewrite cosmic history. If the eighth balance holds, dark energy isn't some late-acting afterthought. It's the latest chapter in a story written at the dawn of time. This could explain why the universe's expansion rate is so finely tuned. Inflation didn't just set the initial conditions, it encoded a feedback mechanism, ensuring future expansion would follow a script written in those first moments. Some theorists even speculate this isn't the first cycle. Perhaps our universe has seen multiple inflationary bursts, each one resetting the cosmic clock while preserving echoes of the past. But the most profound revelation, this balance suggests the cosmos has a kind of memory. The same forces that shaped its infancy still guide its maturity, not as mindless physics but as part of a grand, self-regulating system. It's as if the universe, in its vast complexity, found a way to whisper across 14 billion years, reminding itself, and us, that nothing in its evolution is truly random. Every acceleration, every stretched void, every galaxy spinning in the dark might be part of a rhythm older than time itself. Neutrinos are the universe's quietest particles, so elusive that trillions pass through your body every second without a trace. These ghostly particles, born in the hearts of stars and violent cosmic explosions, barely interact with matter. Yet the ninth cosmic balance suggests they might be silent architects of the universe's fate, subtly tweaking the battle between gravity and dark energy in ways we never imagined. Picture a vast cosmic scale. On one side, gravity pulls matter together with relentless force. On the other, dark energy pushes space apart. Neutrinos could be the almost invisible weights tipping that balance, their faint gravitational influence acting like a dimmer switch on gravity itself. Here's how it might work. Neutrinos come in 3 types or flavors, and they oscillate between these states as they travel near light speed. This oscillation isn't just a quirky particle behavior, it could have cosmic consequences. Recent theories propose that when neutrinos change flavor, they briefly interact with the fabric of space-time in a way that slightly weakens gravity's grip over immense distances. It's as if every neutrino in the universe is a tiny ambassador, negotiating between gravity and dark energy, ensuring neither gains total dominance. The effect is minuscule for a single particle, but multiply it by the countless neutrinos flooding the cosmos, and you've got a force capable of shaping the universe's expansion. The numbers behind this are staggering. Neutrinos outnumber atoms in the universe by 1 billion to 1. Even with their near-zero mass, their collective gravitational influence could be enough to alter how galaxies cluster over billions of years. Some models suggest this neutrino leak in gravity's strength might explain why dark energy began dominating cosmic expansion roughly 5 billion years ago. The timing aligns eerily well with when neutrinos would have cooled enough for their flavor oscillations to reach peak efficiency. It's a cosmic coincidence that feels anything but accidental. What's truly revolutionary is how this balance challenges our understanding of fundamental forces. Gravity has always been seen as a one-way street. Mass warps spacetime, end of story. But if neutrinos can modulate gravity's strength even slightly, it implies a feedback loop we never anticipated. Dark energy's push causes neutrinos to spread out, which in turn weakens gravity's pull, allowing dark energy to push even harder. This self-reinforcing cycle could be the hidden engine driving the universe's accelerating expansion, with neutrinos as the unsung mediators. The implications stretch beyond cosmology. If neutrinos influence gravity on large scales, it could solve mysteries like why some galaxy clusters seem less massive than expected, or why certain cosmic structures appear more spread out than simulations predict. Even more tantalizing, this might be our first clue that gravity isn't as universal as we thought, that its strength varies depending on the quantum dance of particles we're only beginning to understand. So the next time you hear about neutrinos, remember, these aren't just cosmic background noise. They might be the universe's stealthy peacekeepers, ensuring the delicate tension between gravity and dark energy never tips too far in either direction. In a cosmos of unimaginable scales and forces, it's humbling to think that the tiniest, quietest particles could hold the keys to its grandest symmetries. The 10th cosmic balance introduces something chilling, a doomsday scenario called the Big Rip, where dark energy grows so powerful it shreds the very fabric of reality. Imagine spacetime as a stretched rubber sheet. Normally, it bends and warps but holds firm. Now picture that sheet thinning, fraying, until galaxies, stars, even atoms are torn apart in a final, violent crescendo of expansion. This isn't science fiction. Without a crucial check on dark energy's strength, it's the fate some models predict for our universe. But here's the twist. The universe seems to have a built-in failsafe, a phantom energy limit coded into the cosmic rulebook that prevents this apocalyptic finale. This balance works like an invisible pressure valve. As dark energy accelerates the universe's expansion, its density should theoretically decrease unless, that is, it's fueled by something far stranger. Phantom energy, a hypothetical form of dark energy, defies intuition by growing stronger as space expands. Left unchecked, it would eventually overpower every binding force, ripping apart galaxy clusters, then galaxies, then solar systems, and finally the very atoms that make up matter. The mathematics behind this is terrifyingly simple. If the phantom energy parameter, denoted as W, dips below -1, the universe is doomed. Yet every measurement we've taken hovers just above that threshold, as if some unseen hand is holding the line. Why doesn't the universe cross into catastrophic territory? The 10th balance suggests an answer. Dark energy's strength is dynamically regulated by the cosmos itself. Think of it like a cosmic thermostat. When expansion accelerates too quickly, quantum fluctuations in the vacuum of space may generate counteracting forces that stabilize dark energy's growth. Some theories propose this feedback loop is tied to the holographic principle, where information about the universe's energy density is encoded on its boundaries, creating a self-correcting mechanism. Others point to higher dimensional physics, where dark energy's influence leaks into hidden dimensions before it can reach destructive levels. The evidence for this balance is written in the large-scale structure of the universe. If phantom energy were truly unchecked, we'd see voids expanding at wildly different rates, with galaxies torn from their clusters long before their time. Instead, surveys show a remarkable consistency in how structures evolve, as if expansion is being fine-tuned in real time. Even more telling, the cosmic microwave background's subtle patterns align perfectly with models where dark energy's equation of state never crosses the W equals -1 threshold. It's as if the universe has a built-in speed limit preventing its own destruction. What's truly humbling is the precision of this equilibrium. The difference between a stable cosmos and a catastrophic big rip hinges on a value less than 1% from the critical threshold. That razor-thin margin suggests this isn't random luck, it's architecture. Whether through undiscovered physics or some deeper principle, the universe appears programmed to avoid self-destruction. And if that's true, it means the cosmos isn't just expanding. It's evolving with purpose, guided by rules we're only beginning to decipher. So when you gaze at the night sky, remember, the darkness isn't empty. It's alive with invisible safeguards, ensuring the stars keep shining, at least for now. What if our universe isn't the only one, just the only one where life could exist? The 11th cosmic balance plunges us into the multiverse, a sea of possible realities where dark energy's strength varies wildly. In some, it's too weak, collapsing into black holes before stars ignite. In others, it's too strong, scattering matter into cosmic dust before planets form. But ours is the Goldilocks universe, where the numbers align with eerie precision, allowing galaxies to spiral and life to emerge. This isn't just luck, it might be evidence of a deeper filter, a cosmic sieve that only lets finely balanced universes survive long enough to be observed. Think of it like a vast library containing every possible physics textbook. Most are gibberish equations so extreme they describe uninhabitable voids or collapsed singularities. But a handful, by sheer chance, hold the perfect formulas for stability. We exist because we're in one of those rare volumes where gravity and dark energy struck a bargain. The numbers behind this are staggering. Dark energy's observed value is fine-tuned to 1 part in 10 to the power of 120, a precision so absurd it's like hitting a bullseye with a dart thrown from the edge of the observable universe. Random chance can't explain that, but a multiverse can. Here's where it gets controversial. If countless universes bubble into existence, each with random physical constants, most would be stillborn or chaotic. Only those with balances like ours where dark energies push and gravities pull cancel out just enough would last long enough to develop complexity. This idea, called the anthropic principle, suggests our very presence as observers filters the possible realities we could inhabit. We don't see a hostile cosmos because we couldn't exist in one. It's not that the universe was made for life, it's that life only arises in universes that allow it. Critics argue this sounds like giving up on deeper explanations, but the 38 balances offer a twist. They might reveal the mechanism behind this filtering. Certain balances, like the critical density threshold or the expansion structure trade-off, could act as natural selection for universes. Those that fail to meet these criteria vanish instantly, those that pass them persist. Recent string theory models even suggest how this could work: higher dimensional branes colliding to spawn new universes, each inheriting slightly different physics like genetic mutations. Over unimaginable time and trials, stable configurations like ours dominate the multiverse landscape. The implications are staggering. If true, the cosmic balances aren't just local laws, they're universal survival traits. Our universe's dark energy strength isn't arbitrary. It's the winning ticket in a lottery with nearly infinite losers. This doesn't just reshape cosmology. It redefines our place in reality. We're not accidental inhabitants of a random cosmos. We're witnesses to a rare equilibrium, a fleeting moment where the scales tipped just right to let the universe gaze back at itself. And that changes everything. The 12th cosmic balance dares to ask a radical question. What if gravity isn't the unchanging force we've always assumed? For centuries, from Newton's apple to Einstein's warped spacetime, we've treated gravity's strength as a fixed constant, as reliable as the speed of light. But what if it subtly shifts over billions of years, adjusting in lockstep with dark energy to keep the universe in perfect harmony? This isn't just wild speculation. Tiny discrepancies in ancient starlight and the odd behavior of distant galaxies hint that gravity's grip might have been slightly weaker in the early cosmos, just enough to explain why the universe evolved the way it did. Imagine gravity as a cosmic volume knob. Turn it up too high in the universe's youth, and matter would have clumped too quickly, creating oversized black holes instead of galaxies. Turn it down too low and nothing would have coalesced at all. Yet here we are, in a Goldilocks reality where gravity's strength seems exquisitely tuned for structure to emerge. The 12th balance proposes an elegant solution. Gravity isn't set in stone. It's in a slow dance with dark energy, each adjusting to the other's moves like partners in a tango. When dark energy's push strengthens over eons, gravity compensates by weakening just enough to prevent cosmic chaos. Evidence for this hides in the faint afterglow of the Big Bang. The cosmic microwave background shows temperature fluctuations that align suspiciously well with models where gravity was a fraction weaker in the past. Even more telling, the rate at which galaxy clusters grow over time doesn't quite match predictions unless you factor in a slight, gradual change in gravity's strength. It's as if the universe left breadcrumbs for us to follow, clues that the laws we consider immutable might be more like guidelines, flexing to preserve balance on the grandest scales. This idea doesn't just solve cosmic puzzles, it redefines our understanding of physics. If gravity varies even minutely, it implies that constants aren't so constant after all. The implications ripple across disciplines from particle physics to quantum theory. Could other fixed forces like electromagnetism also shift over time? Are we seeing the tip of a deeper principle, a universe where the rules themselves evolve to maintain stability? The beauty of this balance lies in its elegance. Instead of inventing new particles or dimensions to explain cosmic mysteries, it suggests the answers are hiding in plain sight, woven into the very fabric of the forces we thought we knew. So the next time you feel the steady pull of Earth's gravity, remember, that force might be quieter today than it was billions of years ago, its voice softening just enough to let the universe sing in harmony. Entropy might seem like physics' way of saying everything falls apart, the universe's slow march toward chaos, but the 13th cosmic balance flips that notion on its head, revealing entropy not as gravity's enemy but as its silent partner. Picture a cup of hot coffee left on a table. Over time, heat dissipates, steam rises, and the system settles into disorder. That's entropy in action. Now imagine that same principle governing the cosmos, where the spread of energy doesn't just create chaos but shapes the very fabric of space-time. This is the startling idea at the heart of the entropy-gravity connection. That gravity itself might emerge from the universe's relentless drive toward disorder. The math behind this is as elegant as it is radical. In the 1970s, physicist Jacob Bekenstein discovered that black holes have entropy, a measure of their internal chaos proportional to their surface area. Stephen Hawking later showed they also radiate heat, linking thermodynamics to gravity in a way no one expected. Fast forward to today, and the 13th balance takes this further, suggesting that entropy gradients, differences in disorder across space, could generate localized gravitational effects. It's as if gravity isn't a fundamental force at all, but a side effect of the universe's quest for equilibrium, like the way air rushes to fill a vacuum. Here's where dark energy enters the picture. If gravity arises from entropy, then dark energy's accelerating expansion could be the cosmos' way of maximizing disorder on the grandest scale. Think of it like this: as the universe expands, it creates more space, which in turn allows for more possible configurations of matter and energy, more entropy. Dark energy's push might be nature's ultimate entropy engine, ensuring the universe never settles into a stagnant, orderly state. Meanwhile, gravity acts as the counterbalance, clustering matter into galaxies and stars, creating pockets of concentrated entropy like whirlpools in a flowing river. The implications are profound. This balance could finally bridge Einstein's theory of gravity with the laws of thermodynamics, two pillars of physics that have stubbornly resisted unification. It also offers a fresh perspective on dark energy's role. Instead of some mysterious anti-gravity force, dark energy might simply be the universe's tendency to explore every possible state, stretching space-time to accommodate infinite disorder. Some models even suggest that in regions of extreme entropy, like the centers of galaxies, gravity's behavior subtly shifts, aligning with predictions made by this thermodynamic approach. But the real magic lies in the numbers. When physicists calculate the entropy of the observable universe, it's staggeringly large, around 10 to the power of 120 in dimensionless units. Yet this unimaginable number isn't random. It's finely tuned to allow both structure thanks to gravity and expansion thanks to dark energy to coexist. The 13th balance hints that this tuning isn't accidental. It's the universe's way of walking a tightrope between chaos and order, ensuring galaxies can form while still leaving room for entropy to grow. So the next time you see steam rising from your coffee, remember, that same drive toward disorder might be sculpting the cosmos itself. From the spin of galaxies to the acceleration of expansion, entropy isn't just a destroyer. It's a cosmic architect quietly shaping the universe's deepest balances. And if this connection holds, it could rewrite not just our understanding of gravity, but the very nature of reality. Magnetic fields weave through the cosmos like invisible threads, stitching together the vast cosmic web in ways we're only beginning to understand. While gravity and dark energy dominate the conversation about cosmic evolution, the 14th balance reveals something extraordinary. These magnetic fields might be far more than passive bystanders. They could actively shape how dark energy influences the universe, channeling its repulsive force like cosmic riverbanks guiding a powerful current. Picture a spiderweb glistening with morning dew, each strand subtly directing where droplets gather. On a scale billions of times larger, magnetic filaments may similarly steer dark energy's push, determining which regions of space stretch faster and where matter collects into galaxies. The evidence for this comes from some of the universe's most violent phenomena. When astronomers study the aftermath of galaxy collisions or the jets screaming from active black holes, they detect magnetic fields millions of light-years long, far larger than anyone predicted. These colossal structures don't just trace the cosmic web, they seem to reinforce it like steel girders supporting a skyscraper. What's truly groundbreaking is how these fields align with patterns in dark energy's distribution. In regions where magnetic fields are strongest, dark energy's expansion effect appears slightly muted, as if the fields are resisting its push. Meanwhile, in the voids between galaxies where magnetism is weaker, dark energy runs wild, accelerating expansion unchecked. This interaction could solve a long-standing puzzle: why galaxies often form along specific filaments in the cosmic web, rather than scattering randomly. Magnetic fields may act as cosmic traffic controllers, funneling dark energy's repulsion away from developing structures while allowing gravity to work its magic. Computer simulations that include this effect produce uncannily accurate maps of the real universe's large-scale structure, matching observations better than models that treat dark energy as uniform. It's as if the universe has a hidden magnetic blueprint, one that's been subtly guiding its evolution since the first stars flickered to life. The implications stretch beyond galaxy formation. If magnetic fields truly modulate dark energy, they might also influence the universe's ultimate fate. Some theories suggest these fields could grow stronger over time, eventually acting as a cosmic brake on expansion. Others propose they might create localized pockets where dark energies affects very dramatically islands of stability in a sea of accelerating space. Either scenario would rewrite our understanding of cosmic destiny, suggesting the universe's expansion isn't just a simple tug of war between gravity and dark energy, but a complex symphony with magnetism as the conductor. What's humbling is how much we've overlooked. For decades, magnetism was considered a minor player in cosmology, relevant only to stars or planets. Now, the 14th balance suggests it's been shaping the cosmos all along, quietly ensuring that dark energy's chaos doesn't overwhelm gravity's order. So the next time you hear about the cosmic web, remember, it's not just a tapestry of matter and emptiness. It's a living, dynamic structure, vibrating with invisible magnetic forces that may hold the key to why our universe looks the way it does. And that realization changes everything. One of the universe's greatest mysteries isn't just that matter exists, it's that matter exists at all. According to everything we know about particle physics, the Big Bang should have created equal amounts of matter and antimatter, leaving them to annihilate each other in a flash of pure energy. Yet here we are, in a cosmos where matter dominates so completely that antimatter is little more than a rare curiosity. This baffling imbalance, known as baryon asymmetry, defies conventional explanations, but the 15th cosmic balance offers a startling possibility. What if dark energy's subtle pressure in the universe's first moments nudged the scales ever so slightly, ensuring matter's survival against all odds? Picture the infant universe as a seething cauldron of particles and antiparticles popping into existence, only to collide and vanish in bursts of radiation. In these frenzied conditions, even the tiniest asymmetry could mean the difference between a universe brimming with galaxies and one devoid of anything but light. The standard model of physics predicts complete symmetry, so where did the imbalance come from? Some theories point to hypothetical particles decaying unevenly, favoring matter by a hair. Others invoke quantum fluctuations or exotic fields, but the 15th balance introduces a radical alternative. Dark energy's repulsive force, usually associated with cosmic expansion, might have played an unexpected role in those first microseconds. Here's how it could work. During the universe's hyperinflating birth, dark energy's pressure would have stretched spacetime at unimaginable speeds. This expansion wasn't perfectly uniform. Quantum effects would have created microscopic variations in density and energy. In regions where dark energy's push was strongest, particles might have been stretched apart just enough to disrupt the perfect matter-antimatter pairings, allowing a slight excess of matter to escape annihilation. It's like shaking a box of paired magnets. Most stay connected, but a few separate when jostled. Over the entire observable universe, this tiny bias could have snowballed into the overwhelming matter dominance we see today. The evidence for this is written in the stars, literally. If matter and antimatter had perfectly annihilated, the cosmos would be filled with nothing but photons. Instead, we're surrounded by galaxies, planets, and people, all made possible because roughly 1 in a billion matter particles survived that primordial battle. Even more telling, the cosmic microwave background shows faint patterns that align with models where early dark energy perturbations influenced particle physics. It's as if the universe left us a breadcrumb trail back to its first impossible decision, to favor existence over oblivion. This balance doesn't just solve a cosmic puzzle, it redefines dark energy's role in creation. No longer just an afterthought pushing galaxies apart, it emerges as a midwife to reality itself, shaping the conditions for matter's survival. Without its subtle intervention, the universe might have remained a featureless void, devoid of stars, planets, or life. So when you look around at the world, at the trees, the mountains, the screen in front of you, remember, you're not just seeing matter, you're witnessing the aftermath of the universe's first and most consequential imbalance, a fleeting asymmetry frozen in time, echoing across 14 billion years. Deep in the cosmic void, something strange is happening. Galaxy clusters aren't just drifting apart with the universe's expansion. They're moving together as if pulled by an invisible hand. Astronomers call this eerie motion the dark flow, and it defies everything we know about cosmic dynamics. These clusters, some containing thousands of galaxies, stream in the same direction at staggering speeds, over 2 million miles per hour, toward a point beyond the edge of our observable universe. The 16th cosmic balance offers a spine-tingling explanation. Dark energy might not be uniform. Instead, it could flow in vast, unseen currents, carrying galaxies along like leaves in a cosmic river. What makes this phenomenon so unsettling is its scale. The dark flow isn't local, it stretches across billions of light years, affecting clusters as far as we can observe. Gravity alone can't explain it. Even the pull of known superclusters, the largest structures in the universe, falls short by orders of magnitude. That leaves only two possibilities. Either our measurements are catastrophically wrong, or something outside our cosmic horizon, a structure so colossal it dwarfs the observable universe, is exerting gravitational influence. The 16th balance leans toward the latter, proposing that dark energy's repulsive force might interact with these hidden megastructures, creating directional ripples that nudge galaxies off course. Here's where it gets even stranger. If dark energy flows unevenly, it could mean the universe beyond our view isn't just more of the same. There might be regions where dark energy's strength varies dramatically, like cosmic weather patterns, high-pressure zones pushing galaxies in specific directions. Some theorists speculate these flows could trace back to the Big Bang's earliest moments, when quantum fluctuations left imprints that grew into vast, invisible gradients over billions of years. Others suggest they're evidence of neighboring universes in the multiverse, their gravity subtly leaking into ours like echoes through a cosmic curtain. The evidence is tantalizing but contentious. When researchers first detected the dark flow in 2008 using the cosmic microwave background as a reference frame, skepticism ran high. Could instrument errors or overlooked astrophysical effects mimic such a signal? Yet subsequent studies, including observations of hundreds of galaxy clusters by the Planck satellite, found the same peculiar motion. The odds of this being a fluke are vanishingly small, less than 1 in a million. That doesn't mean the dark flow is proven, but it does mean we can't ignore it. This balance doesn't just challenge our models, it redefines the playing field. If confirmed, the dark flow implies that the universe isn't just expanding, it's being sculpted by forces we can't see, from realms we can't reach. It's like standing on a beach, feeling the tide pull at your feet, while knowing the ocean stretches far beyond the horizon. Only here, the ocean is space-time itself, and the tides are woven from dark energy's hidden currents. And if we follow those currents, they might just lead us to the greatest discovery in cosmology, proof that our universe isn't alone. Black holes don't die quietly. When two of these cosmic behemoths spiral toward each other, their collision sends shockwaves rippling through space-time itself, gravitational waves that stretch and squeeze everything in their path. These waves, first detected in 2015 by LIGO, opened a new window into the universe's most violent events. But the 17th cosmic balance suggests something even more profound. Hidden within these ripples could be dark energy's fingerprints, subtle distortions revealing how this mysterious force interacts with gravity in the most extreme environments imaginable. Think of it like listening to a bell ringing in a vast, empty cathedral. The sound carries echoes of the space around it, the height of the ceilings, the shape of the walls. Gravitational waves work the same way. As they travel across the universe, dark energies push against space-time, leaves faint imprints on their waveform, like invisible hands brushing against a vibrating string. The math behind this is elegant yet mind-bending. Normally, gravitational waves lose energy as they travel, their amplitude fading with distance. But if dark energy interacts with them directly, certain frequencies could get a slight boost, or the wave's shape might twist in telltale ways. These deviations would be tiny, far smaller than current detectors can spot, but future observatories, like the space-based LISA mission or next-generation ground-based arrays, might catch them. What makes this balance so revolutionary is its potential to solve a major cosmological puzzle. Right now, we measure dark energy's effects indirectly by observing how fast galaxies recede from us. But gravitational waves offer something entirely new, a direct probe of how dark energy behaves in regions of extreme gravity, like near black hole mergers. If the 17th balance holds, these waves could reveal whether dark energy's strength changes in the presence of intense gravitational fields, a clue that it's not a static force, but something dynamic and interactive. The implications stretch far beyond astrophysics. If dark energy leaves signatures in gravitational waves, it might finally explain why this force seems fine-tuned to allow galaxies and life to exist. Some models suggest these distortions could even hint at dark energy's origins, whether it emerges from quantum vacuum fluctuations, higher dimensional physics, or something even stranger. And if the patterns match predictions from the 38 balances, It would be smoking gun evidence that these principles aren't just mathematical curiosities, they're the universe's hidden operating system. Imagine a future where every black hole collision doesn't just tell us about gravity, but acts as a cosmic messenger, carrying encrypted notes about dark energy's role in shaping reality. We're on the verge of decoding those messages, and when we do, the answers might rewrite everything we thought we knew about the forces governing existence. Until then, every ripple in spacetime is a tantalizing hint, a whisper from the dark that we're only just learning to hear. The 18th cosmic balance plunges us into one of physics' most radical ideas, that our three-dimensional universe might be a hologram, an illusion projected from information encoded on a distant two-dimensional surface. Picture your entire reality, the stars, planets, even the screen you're watching right now, as nothing more than a shimmering mirage like light dancing on the surface of a pond. This holographic principle, born from black hole physics and string theory, suggests that gravity and dark energy aren't fundamental forces at all. Instead, they could emerge from something far stranger, a cosmic code written in the language of quantum bits on the universe's outermost boundary. Here's where it collides with dark energy in the most unexpected way. If the universe truly is a hologram, then dark energy's accelerating expansion might not be driven by some mysterious substance filling space. It could be a side effect of how information gets processed on that primordial 2D surface, like pixels straining to render an increasingly complex simulation. The math behind this is staggering. Calculations show that when you apply holographic principles to cosmology, dark energy naturally arises as a consequence of the boundary's limited information density. It's as if the universe has a built-in resolution limit, and dark energy is what happens when reality tries to expand beyond its own encoding capacity. This balance doesn't just rewrite the rules, it redefines the playing field. Normally, we think of gravity and dark energy as opposing forces battling across spacetime. But in the holographic view, they're two sides of the same coin, both emerging from deeper information dynamics. Imagine a movie projected on a screen. Gravity would be the way objects in the film appear to interact, while dark energy is the subtle warping of the projector's lens. Neither is real. In the traditional sense, both are artifacts of a more fundamental process happening behind the scenes. Evidence for this wild idea hides in the cosmic microwave background. Those faint temperature fluctuations, the universe's baby picture, display statistical patterns eerily similar to what holographic models predict. Even more compelling, the way black holes behave. Their entropy, a measure of internal chaos, is proportional to their surface area, not their volume, as if all their information is painted on their event horizons. If black holes, the densest objects in existence, can be described as holograms, why not the entire cosmos? The implications are dizzying. If the 18th balance holds, dark energy isn't some exotic substance, it's a cosmic glitch, a sign that reality is running up against its own informational limits. It would mean the universe isn't just expanding, it's recalculating itself in real time, stretching its code to accommodate new complexity. And somewhere, on a boundary we can't see or reach, every galaxy, every atom, every thought you've ever had is being rendered instant by instant, a shadow play on the edge of existence. So when you gaze at the night sky, remember, you might not be looking out into space at all. You could be peering inward at a reflection of reality's deepest layer, a universe written in light on the walls of infinity. Quantum physics tells us that empty space is anything but empty. It's a seething, bubbling froth of virtual particles blinking in and out of existence so fast we can't detect them directly. These fleeting fluctuations generate what's called vacuum energy, a background hum of the universe that should, by all calculations, be unimaginably strong. Here's the paradox: when physicists crunch the numbers, the predicted energy of this quantum froth is a staggering 120 orders of magnitude stronger than what we actually observe in the cosmos. That's like calculating the power of a hurricane but measuring a gentle breeze, a discrepancy so vast it's been called the worst theoretical prediction in the history of science. The 19th cosmic balance offers a way out of this crisis, revealing how the universe might have fine-tuned this vacuum energy to precisely match the measured strength of dark energy. Picture the quantum vacuum as an ocean in constant turmoil, waves crashing in all directions with unfathomable energy. If even a fraction of this energy manifested as Einstein's cosmological constant, the repulsive force would have ripped the universe apart before atoms could form. Yet somehow, against all odds, the vacuum energy we observe is extraordinarily weak, just strong enough to explain dark energy's gentle nudge on cosmic expansion. This isn't just luck. The balance suggests an ingenious solution. What if most of that theoretical vacuum energy gets screened out by an unknown mechanism, leaving only the tiny residual we detect as dark energy? Think of it like noise-canceling headphones for the cosmos, an invisible filter that silences the quantum cacophony, allowing only the faintest whisper to influence the universe's expansion. The evidence for this balancing act comes from multiple directions. First, the measured value of dark energy aligns suspiciously well with theoretical estimates for the vacuum energy's residual effects after such screening. Second, certain unified field theories predict symmetry-breaking mechanisms that could naturally suppress vacuum energy to the observed levels. But the most compelling clue comes from the cosmic microwave background. Its subtle temperature variations match simulations where vacuum energy is dynamically adjusted rather than fixed. It's as if the universe has an automatic volume control, turning down the background energy to prevent cosmic catastrophe. What's truly revolutionary is how this balance could solve multiple puzzles at once. Not only does it reconcile quantum theory with cosmological observations, but it also explains why dark energy became dominant exactly when it did around 5 billion years ago. As the universe expanded and cooled, the screening mechanism's efficiency might have gradually changed, allowing the residual vacuum energy we call dark energy to finally make its presence known. This timing isn't random, it's the moment when galaxies had already formed, when cosmic structures were mature enough to resist being torn apart by the newfound push. Critics argue this sounds like fine-tuning by another name, but the 19th balance suggests a deeper principle at work. The screening mechanism might emerge naturally from higher dimensional physics or quantum entanglement effects, making the apparent tuning inevitable rather than miraculous. Some models even propose that the same process that suppressed vacuum energy also shaped the early universe's inflation, linking two of cosmology's greatest mysteries in a single framework. So the next time you hear that space is empty, remember, it's actually a maelstrom of quantum energy, carefully filtered and balanced to allow galaxies, stars, and life itself to exist. The vacuum energy paradox isn't just a theoretical headache. It's a clue that the universe operates with hidden precision, turning what should have been a cosmic disaster into the gentle force we call dark energy. And that realization changes how we see everything, from the vast expanse between galaxies to the seeming nothingness in the palm of your hand. We live in a universe that seems tailor-made for life, a reality where gravity's pull and dark energy's push have struck a balance so precise it borders on the miraculous. Tweak either force even slightly and the cosmic stage collapses, Stars flicker out before they ignite, planets never coalesce, and life becomes impossible. This isn't just philosophical musing. The 20th cosmic balance confronts us with a staggering truth. Our existence hinges on a razor's edge of physical constants, and dark energy's delicate dance with gravity might be the reason why. Consider the numbers. Dark energy's observed strength is fine-tuned to 1 part in 10 to the power of 120. That's like balancing a pencil on its tip for billions of years while hurricanes rage around it. If dark energy were stronger by a hair, its repulsive force would have ripped apart proto-galaxies before they could form. Weaker, and gravity would have crushed the universe into a black hole before the first stars burned. Yet here we are in a Goldilocks zone where both forces cancel out just enough to allow complexity and life to emerge. This precision isn't limited to dark energy. Gravity's strength, the mass of elementary particles, even the nuclear forces that power stars all seem calibrated within impossibly narrow margins. Change any by a few percent, and carbon atoms, the backbone of life, wouldn't form in stellar furnaces. Water wouldn't expand when frozen, preventing Earth's oceans from solidifying. Even the geometry of space-time would warp, disrupting the stable orbits planets rely on. The 20th balance suggests this isn't coincidence. It's the universe's way of filtering out uninhabitable realities, leaving only those where forces align to permit observers like us to exist. Critics argue this reasoning is circular. Of course, we find ourselves in a life-friendly universe. We couldn't observe one that wasn't, but the balance goes deeper. It predicts that any universe capable of generating complexity must exhibit certain properties, like a near-perfect equilibrium between expansion and contraction. Observations bear this out. From the flatness of spacetime to the abundance of heavy elements, our cosmos fits the profile of a universe engineered not by a designer, but by the sheer statistics of possibility. In a multiverse of infinite variations, only those with such balances ever develop astronomers to notice them. The implications are humbling. Dark energy isn't just some abstract force accelerating galaxies. It's the linchpin in a cosmic equation that makes our existence possible. Every planet, every living cell, every thought ever thought owes itself to this precarious equilibrium, a reminder that the universe isn't just a place. It's a process, one that seems almost intent on creating conditions where it can look back at itself and wonder why. What if gravity and dark energy aren't the only players in this cosmic tug of war? The 21st balance dares to imagine something radical, a fifth fundamental force, an unseen hand quietly mediating between these titans. We've grown up learning about nature's 4 forces: gravity, electromagnetism, and the strong and weak nuclear forces. But hidden in the gaps between galaxies, in the way dark energy's push seems to fluctuate where gravity is strongest, there might be whispers of something new, a force that doesn't fit the known rules. Picture this hypothetical force as a cosmic negotiator, stepping in when gravity and dark energy threaten to destabilize the universe's delicate equilibrium. Unlike gravity's relentless pull or dark energy's expansive push, this fifth interaction could act more like a moderator, softening their extremes. Some theories suggest it might only activate over vast distances, explaining why we haven't detected it in Earth-bound experiments. Others propose it's tied to dark matter, emerging only when certain densities of matter or energy are present. The implications are staggering because if such a force exists, it would rewrite the textbooks overnight. Clues for this idea lurk in astronomical anomalies. Take galaxy rotation curves. Stars orbit their galactic centers so fast that, according to known physics, they should fling into the void. Dark matter explains part of this. But what if an additional force is subtly altering gravity's grip at these scales? Or consider the way some galaxy clusters seem to move with eerie coordination, as if connected by invisible threads. The standard model can't fully account for these behaviors, but a fifth force tuned to interact with both dark matter and dark energy just might. The math behind this balance is both elegant and speculative. Unlike the other forces, this one wouldn't diminish with distance in the usual way. Instead, it might strengthen in the presence of dark energy's stretching effect, creating a feedback loop that stabilizes cosmic structures. Imagine a rope tied between two tug-of-war teams. When one side pulls too hard, the rope tightens, redistributing the tension. That's the kind of dynamic equilibrium this force could provide, preventing either gravity or dark energy from gaining total dominance. Critics argue that inventing new forces is a slippery slope, a fix for every unexplained phenomenon, but proponents counter that history favors the bold. When Mercury's orbit defied Newton's predictions, we didn't discard gravity, we discovered relativity. When atomic behavior baffled physicists, quantum mechanics emerged. The fifth force hypothesis follows this tradition, daring to explore the gaps in our understanding rather than papering them over. And here's the most tantalizing part: we might not need to wait decades to test this. Upcoming experiments like the European Space Agency's Euclid telescope or the Vera Rubin Observatory's sky surveys could spot subtle distortions in spacetime that betray this force's presence. If they do, it won't just solve the dark energy gravity puzzle, it'll open a portal to a whole new layer of reality, one where the universe's deepest balances are maintained by forces we're only beginning to dream of. The cosmic microwave background isn't just a relic of the Big Bang, it's the universe's first love letter, etched in microwaves and whispered across 14 billion years. This faint glow, the afterglow of creation itself, holds secrets about dark energy's role in shaping reality, hidden in patterns so subtle they were invisible until satellites like Planck mapped them with quantum precision. The 22nd cosmic balance deciphers these patterns, revealing how microscopic ripples in the newborn cosmos set the stage for the delicate equilibrium between dark energy and gravity we see today. Think of the CMB as a snapshot of the universe at just 380,000 years old, a time when space transitioned from an opaque plasma to a transparent sea of atoms. The temperature variations in this ancient light, some warmer, some cooler by mere millionths of a degree, aren't random noise. They're frozen echoes of quantum fluctuations from the universe's first trillionth of a second, stretched to cosmic scales by inflation. These tiny seeds grew into the galaxies and voids we see today, but here's the twist: their distribution isn't just a blueprint for matter. It's a cipher for dark energy's influence. The balance emerges when you compare these primordial patterns to the universe's current structure. Certain large-scale features like the apparent lumpiness of galaxy clusters or the spacing between superclusters align too perfectly with CMB fluctuations to be coincidence. Dark energy seems to have subtly sculpted this evolution, acting like an invisible hand guiding how those early ripples blossomed into the cosmic web. It's as if the universe's infancy contained cryptic instructions for its adulthood, with dark energy as the executor of that cosmic will. One of the most startling clues lies in the CMB's cold spot, a mysterious region unusually devoid of microwaves. Some theories suggest this could be a bruise left by dark energy's early tug-of-war with gravity, a pocket where expansion briefly overwhelmed attraction, leaving a void that persists to this day. Other anomalies, like unexpected alignments in the polarization of CMB light, hint that dark energy might have interacted with spacetime in ways we're only beginning to model. These aren't just curiosities, they're breadcrumbs leading to a deeper truth. that dark energy's role was written into the cosmos from the very beginning. What makes this balance revolutionary is its predictive power. By reverse engineering the CMB's patterns, cosmologists can test theories about dark energy's nature. For instance, if dark energy's strength has changed over time, it would leave distinct fingerprints in how those ancient fluctuations evolved. Current data suggests it's been eerily constant, but future observations, like those from the Simons Observatory or next-generation space telescopes, might reveal subtle shifts confirming it's more dynamic than we thought. The cosmic microwave background is more than a window to the past. It's a mirror reflecting dark energy's quiet mastery over cosmic destiny, proving the universe didn't just stumble into balance, it was orchestrated from the first moment of existence. And every time we map its faint whisper, we're not just studying history, we're decoding the universe's operating manual, one microwave photon at a time. Neutron stars are nature's ultimate tightrope walkers, cosmic remnants so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. These stellar corpses, born from the explosive deaths of massive stars, exist in a state of perpetual near collapse, their gravity pressing inward with such ferocity that protons and electrons fuse into neutrons, packing an entire sun's worth of mass into a sphere no wider than a city. But here's where the cosmic tightrope gets even more precarious. There's a limit to how dense these objects can become, a boundary where gravity's crushing grip meets an unexpected counterforce, dark energy's subtle push from the void. The 23rd balance reveals this tipping point with startling precision. As a neutron star condenses, its gravity warps spacetime so severely that dark energy's repulsive effect, usually negligible on small scales, begins to amplify. Picture a rubber sheet stretched to its limit. Gravity pulls matter inward, dimpling the fabric of space, while dark energy's anti-gravity push resists from below, preventing the sheet from tearing. For neutron stars, this equilibrium defines a universal size limit around 2.5 times the mass of our Sun. Beyond that threshold, the star's own gravity would overcome even the nuclear forces holding it together, triggering a catastrophic collapse into a black hole. This balance isn't just theoretical. Observations of neutron stars like the famous PSR J0740 plus 6620, a pulsar weighing in at just under that critical limit, align eerily well with predictions. Even more compelling, the absence of neutron stars larger than this limit in surveys of the Milky Way. It's as if the universe has drawn a line in the sand, forbidding these objects from growing too massive without crossing the point of no return. What's truly remarkable is how this interplay reflects the larger cosmic dance. Dark energy, often dismissed as relevant only on galactic scales, proves it has a role to play even in the most extreme gravitational environments. Its push might be minuscule compared to a neutron star's gravity, but at the quantum level, it's enough to tip the scales. Some models suggest this balance could even explain why black holes of certain sizes are rarer than expected. Dark energy's influence might subtly alter the conditions for their formation. So the next time you hear about a neutron star's mind-bending density, remember, you're not just learning about a dead star, you're witnessing a microcosm of the universe's grandest balancing act, where the weakest and strongest forces in nature negotiate a truce, ensuring reality stays stable, one stellar corpse at a time. Galaxies spin with a grace that defies simple physics. Stars at their outer edges whip around at speeds that should send them hurtling into the void. According to Newton's laws, the visible mass of a galaxy, its stars, gas, and dust shouldn't provide enough gravity to keep these stars anchored. Yet they cling to their orbits, held by something unseen. For decades, dark matter has been the go-to explanation. an invisible scaffold of particles adding the extra gravitational glue. But the 24th cosmic balance offers a radical alternative. What if dark energy's subtle push combined with gravity is the hidden hand guiding these stars? Imagine a galaxy as a spinning carousel. The riders near the center move slowly while those at the edge whip around faster. But in a galaxy, the outer stars don't slow down as expected. They maintain blistering speeds as if an unseen force is subtly nudging them along. Dark matter theories propose an invisible halo surrounding the galaxy, adding mass and therefore gravity. But there's another possibility. Dark energy, usually thought of as a large-scale force driving galaxies apart, might have a localized effect, acting like a gentle tailwind against gravity's pull. This wouldn't cancel gravity out, it would redistribute its influence, altering how stars experience the galaxy's tug. The math behind this is delicate but compelling. If dark energy's repulsive force interacts with galactic gravity in just the right way, it could create a dynamic where stars farther from the center experience a slight reduction in effective gravitational pull. This wouldn't replace dark matter entirely. Some of its effects are still needed to explain other phenomena, but it could mean dark energy plays a far more nuanced role than we've assumed. Think of it like sailing. Gravity is the ocean current pulling you forward, while dark energy is the wind at your back, subtly altering your speed without changing your direction. Evidence for this idea is emerging from unexpected places. Some galaxies show rotation curves, the graph of star speeds versus distance from the center, that don't quite match pure dark matter predictions. In these cases, adding dark energy's push to the equation brings models closer to observations. Even more intriguing, galaxies in regions where dark energy's influence is stronger, like the sparse outskirts of galaxy clusters, show slightly different rotation patterns than those in denser environments. It's as if the universe is giving us hints that dark energy's role isn't just about expansion, it's woven into the very fabric of galactic motion. What's at stake here isn't just a tweak to astrophysics textbooks. If dark energy and gravity jointly govern galactic rotation, it would mean these two forces aren't just opposing each other on cosmic scales, they're collaborators, shaping the universe at every level. It's a vision of reality where the same push driving galaxies apart also helps stars stay in orbit, a cosmic irony so perfect it feels like the universe is playing a joke on us. And if we can decode this balance, we might finally understand why galaxies spin the way they do, not as isolated islands of matter, but as dynamic players in a much larger, more intricate dance. Quantum mechanics and gravity have been the ultimate frenemies of physics, two towering theories that refuse to play nice. On one hand, quantum mechanics rules the subatomic world, where particles pop in and out of existence and reality blurs into probability. On the other, Einstein's gravity sculpts the cosmos, bending spacetime into majestic curves around stars and galaxies. For over a century, physicists have struggled to unite these frameworks, searching for a theory of quantum gravity that could explain everything from black holes to the Big Bang. But the 25th cosmic balance throws a lifeline into this theoretical quagmire. Dark energy, the universe's most enigmatic force, might be the bridge we've been missing. Here's the tantalizing clue. Dark energy's behavior mirrors quirks we typically associate with quantum mechanics. Its energy density remains constant as the universe expands, like an infinite reservoir replenishing itself, a hallmark of quantum vacuum fluctuations. Yet its effects emerge on cosmic scales, shaping the fate of galaxies and the fabric of spacetime itself. This dual nature, quantum at heart, gravitational in effect, suggests dark energy isn't just another player in the cosmic tug of war. It could be the Rosetta Stone translating between the infinitesimally small and the astronomically large. Imagine space-time as a vast, rippling ocean. Quantum mechanics describes the chaotic froth of individual waves, particles appearing and vanishing in a nanosecond dance. Gravity governs the ocean's tides, the slow, majestic swells that move continents. Dark energy, in this analogy, would be the hidden currents connecting the two, ensuring the frenzy of the waves doesn't disrupt the stability of the tides. The math behind this is still speculative, but some theories propose that dark energy arises from quantum entanglement, the eerie link between particles that persists across vast distances. If true, it would mean the universe's expansion is driven, at least in part, by subatomic relationships stretching to cosmic proportions. Evidence for this idea lurks in the universe's large-scale structure. The distribution of galaxies and voids aligns suspiciously well with models where quantum-scale effects leak into gravity's domain via dark energy. Even more compelling, the way dark energy's strength seems fine-tuned to allow galaxy formation. If it were stronger, quantum fluctuations would have overwhelmed gravity in the universe's infancy, preventing matter from clumping. Weaker, and gravity would have crushed everything into black holes before stars could ignite. This precision hints at a deeper dialogue between quantum and gravitational forces, one mediated by dark energy's balancing act. The implications are staggering. If dark energy truly bridges quantum mechanics and gravity, it could solve some of physics' thorniest puzzles. Why do black holes radiate energy? How did inflation launch the universe's expansion? What happens to spacetime at the Planck scale? These questions might all trace back to dark energy's dual citizenship in the quantum and cosmic realms. Future experiments like gravitational wave detectors sensitive to quantum spacetime foam or telescopes mapping dark energy's distribution with unprecedented precision could soon put this idea to the test. So while physicists once saw dark energy as a latecomer to the cosmic party, an afterthought tacked onto Einstein's equations, the 25th balance suggests it might be the guest of honor, the missing link in a theory of everything. And if we're right, this invisible force isn't just pushing galaxies apart, it's whispering the secrets of quantum gravity, waiting for us to listen. Wormholes have long been the stuff of science fiction, cosmic shortcuts bending space and time to connect distant points in the universe. But what if these space-time tunnels aren't just fantasy? The 26th cosmic balance reveals a startling possibility. Dark energy, the same force accelerating the universe's expansion, might hold the key to stabilizing these hypothetical passages. Here's the catch. According to Einstein's equations, wormholes would collapse instantly without something exotic propping them open, a form of matter or energy with negative pressure, repelling gravity instead of attracting it. For decades, physicists dismissed this as impossible, a mathematical curiosity with no basis in reality. Then came dark energy. Measurements show it behaves exactly like the exotic energy wormholes would need, exerting negative pressure on spacetime itself. The coincidence is too striking to ignore. Could the force pushing galaxies apart also be the glue holding interstellar shortcuts together? The math behind this balance is both elegant and mind-bending. A stable wormhole requires its throat, the narrowest part of the tunnel, to be lined with exotic matter, counteracting the crushing force of gravity trying to snap it shut. Dark energy fits the bill perfectly. Its repulsive effect could act like cosmic scaffolding, preventing collapse while keeping the passage navigable. Simulations suggest that in regions where dark energy's density is finely tuned, microscopic wormholes might naturally emerge from the quantum foam, flickering in and out of existence. Scale this up and you've got a potential stargate if only we could control it. But here's where it gets even wilder. If dark energy stabilizes wormholes, it could explain why we haven't detected them. They might not be rare, just invisible, hidden in plain sight. Like bubbles in a boiling pot, they could be constantly forming and popping across the cosmos, their entrances and exits shifting too rapidly to spot. Some theories even propose that dark energy's acceleration isn't uniform but concentrated along these hidden filaments, like water flowing through underground channels. The implications are staggering. A universe threaded with stable wormholes wouldn't just revolutionize travel, it would redefine causality itself. Time dilation, parallel universes, even the nature of black holes might need re-evaluating through this lens. And while we're far from building our own stargates, the mere possibility that dark energy could make them viable changes how we see the cosmos. It's no longer just empty space between stars, it's a dynamic network of potential pathways waiting for us to decode the rules. So the next time you gaze at the night sky, remember, the universe might be far more connected than it appears, with dark energy as the invisible architect of its hidden bridges. The equation that governs dark energy's behavior is deceptively simple. A single variable, W, representing the ratio of its pressure to its energy density. Yet this unassuming symbol holds the fate of the cosmos in its grip. If W were exactly -1, dark energy would behave like Einstein's cosmological constant, a steady force unchanging over time. But if it deviates even slightly, the universe's future swings between two extremes: runaway expansion tearing space-time apart, or a sudden collapse crushing everything back into a singularity. The 27th cosmic balance reveals the astonishing truth: our measurements place W within a hair's breadth of that critical value, as if the universe has a built-in failsafe against self-destruction. Think of W as a cosmic thermostat. Set it too low, say -1.1, and dark energy's repulsive strength grows exponentially with time, leading to the infamous Big Rip, where galaxies, stars, and even atoms are shredded by accelerating expansion. Nudge it too high, -0.9, and dark energy weakens, allowing gravity to gain the upper hand, reversing expansion into a catastrophic Big Crunch. The margin for error is vanishingly small. Current observations constrain W to -1 plus or -0.05, a precision akin to balancing a pencil on its tip for billions of years. What's truly baffling is how this precision persists across cosmic history. When astronomers studied dark energy's effects in the early universe using baryon acoustic oscillations, frozen ripples in the distribution of galaxies, they find the same W value as when measuring nearby supernova. This consistency defies naive expectations. Most physical forces evolve as the universe ages. Gravity weakens with distance. Nuclear forces operate only at tiny scales. But dark energy's equation of state appears locked in place, as if governed by a deeper principle we've yet to uncover. Theories abound to explain this fine-tuning. Some propose W isn't a constant at all, but a dynamic field that adjusts itself to maintain equilibrium, like a river carving its own channel. Others suggest it's fixed by higher dimensional physics or quantum entanglement effects operating across the universe. The most radical idea, that W's value is a selection effect in a multiverse of infinite possibilities. Only universes with W near -1 develop observers capable of measuring it. Whatever the explanation, this balance isn't just academic. It shapes the universe's very structure. A slightly more negative W would have prevented galaxy formation, leaving the cosmos a featureless void. A less negative one might have triggered premature collapse. Instead, we inhabit a reality where W's razor-thin margin allows complexity and life to emerge. So when physicists measure this number with ever greater precision, they're not just solving equations. They're decoding the universe's deepest survival strategy, written in the language of pressure, density, and the invisible force that holds the stars at bay. Galaxies breathe, not in the way living things do, but through vast rivers of gas streaming in and out of their spiral arms, cosmic winds shaped by the violence of newborn stars and the fury of supermassive black holes. These galactic winds should tear galaxies apart, scattering their star-forming fuel into the void. Yet somehow they don't. The 28th cosmic balance uncovers why. These chaotic outflows are precisely tuned to counteract dark energy's large-scale push, creating a self-regulating system where local and cosmic forces dance in lockstep. Picture a galaxy like our Milky Way as a flickering candle in a cosmic breeze. Each time a star ignites or a black hole feasts on surrounding matter, it sends shockwaves through the galaxy's gas reservoirs, blowing material outward at millions of miles per hour. These winds should spell disaster, starving galaxies of the raw materials needed to forge new stars. But here's where dark energy enters the equation. As these winds race outward, they encounter the subtle but relentless pressure of dark energy's expansion, a force acting like an invisible barrier, gently redirecting the ejected gas back toward the galaxy over millions of years. It's as if the universe has installed a cosmic recycling system where nothing truly escapes, only circles back in time. This balance isn't just theoretical. Observations of distant galaxies reveal a striking pattern. The most active star-forming galaxies, those with the fiercest winds, are often surrounded by enormous halos of gas hovering just beyond their gravitational grasp. Instead of vanishing into intergalactic space, this material lingers, waiting to be pulled back in when the galaxy's next cycle of star formation begins. Simulations show that without dark energy's push, these gas halos would disperse entirely, leaving galaxies gasping for fuel. With it, they act like reservoirs, ensuring galaxies never fully exhaust their stellar fuel supply. The numbers behind this are mind-bending. For the balance to hold, the energy carried by galactic winds must match to within a few percent the work required to overcome dark energy's outward pressure in their local environment. Too weak and the gas escapes forever. Too strong and it collapses back too quickly, stifling future star formation. Yet across galaxies of all sizes, from dwarf irregulars to colossal ellipticals, this equilibrium persists. It's as if the universe has calibrated its forces to maintain a perfect feedback loop, where the violence of creation and the patience of cosmic expansion exist in harmony. What's truly revolutionary is how this balance bridges scales. The same force accelerating the universe's expansion also governs the fate of individual galaxies, linking the microscopic physics of supernova explosions to the grand geometry of spacetime. When a massive star dies in a fiery supernova, its shockwaves don't just shape its home galaxy, they ripple through the cosmic web, subtly resisting dark energy's pull on scales billions of times larger. This isn't just astrophysics, it's cosmic poetry, a reminder that the universe operates not as a collection of isolated parts, but as an interconnected whole, where even the smallest events echo across eternity. So the next time you gaze at the Milky Way's shimmering band, remember, those stars aren't just burning in isolation. They're part of a grand, self-sustaining cycle, one where the galaxy's fiery breath meets the universe's silent push, and in that meeting finds balance. In the seething chaos of the early universe, mere moments after the Big Bang, pockets of unimaginable density may have collapsed directly into black holes, not the stellar mass giants we know today, but minuscule ones, some no heavier than an asteroid and smaller than an atom. These primordial black holes, if they exist, would be cosmic relics from a time when the universe was 1 trillion degrees hot and space itself was still settling into its current form. The 29th cosmic balance proposes something extraordinary. These ancient black holes might still be lurking in the darkness, quietly siphoning dark energy from the fabric of space and acting as the universe's hidden regulators. Think of them as cosmic sponges, as dark energy stretches the universe, accelerating galaxies apart. Primordial black holes could be absorbing traces of it, converting that repulsive force into mass through their immense gravitational pull. This wouldn't stop expansion. Dark energy's dominance is too vast, but it might fine-tune its effects, preventing runaway acceleration that could tear reality apart. The math behind this is as elegant as it is speculative. Unlike their larger cousins, primordial black holes wouldn't devour matter in dramatic bursts. Instead, their quantum-scale interactions with dark energy could create a subtle feedback loop. As dark energy's density increases, so does the black hole's absorption rate, naturally balancing the system over eons. Evidence for this idea is tantalizingly indirect. Some regions of the universe show unexpected variations in dark energy's apparent strength, as if something is subtly redistributing its influence. Meanwhile, mysterious gravitational lensing events, brief flashes of distorted light from distant stars, hint at invisible, compact objects drifting through interstellar space. Could these be the fingerprints of primordial black holes, their gravity warping light while their dark energy appetite goes unnoticed? Even more compelling is the way this balance could solve multiple cosmic puzzles at once. If primordial black holes absorb dark energy, their mass would grow over time, potentially explaining why we haven't spotted them yet. They might be just shy of detectable thresholds. But the real magic lies in the implications. If this balance holds, the universe isn't just expanding, it's self-correcting, with ancient black holes acting as cosmic pressure valves. Every time dark energy's push grows too strong, these relics from the dawn of time might quietly step in, ensuring the universe never tips into chaos. It's a breathtaking vision of cosmic equilibrium, where the smallest and most exotic objects in existence play a pivotal role in shaping the fate of everything. And if we're right, the darkness between stars isn't empty, it's alive with invisible architects working in silence to keep the cosmos in check. Light speed isn't just a number on a page, it's the universe's ultimate speed limit, the unbreakable rule that keeps reality from unraveling. At exactly 299,792,458 meters per second, light's constancy underpins everything from the GPS in your phone to the stability of atoms. But here's the cosmic catch. This speed depends on the fabric of spacetime itself, and dark energy is stretching that fabric like taffy. The 30th balance reveals a breathtaking truth. Dark energy's expansion is fine-tuned to preserve light speed, ensuring the laws of physics don't collapse under the strain of an accelerating cosmos. Picture a runner on a treadmill that's speeding up. If the belt accelerates too quickly, the runner stumbles, unable to maintain pace. Now imagine that runner is light, and the treadmill is space-time, with dark energy cranking up the speed. If dark energy's push were even slightly stronger, the stretching of space could alter light's speed over vast distances, throwing relativity into chaos. Electromagnetic forces would falter, atomic bonds would destabilize, and the universe as we know it would cease to function. Yet none of this happens. Despite dark energy's dominance, light speed remains rock steady. a testament to an invisible hand adjusting the treadmill's speed in perfect sync with the runner's stride. This balance isn't just theoretical. Observations of distant quasars, brilliant beacons from the early universe, show their light arriving at precisely the expected speed, even after traveling billions of years through expanding space. Even more telling, the behavior of cosmic rays and gamma-ray bursts aligns perfectly with models where dark energy's expansion rate is calibrated to preserve light's constancy. It's as if the universe has a built-in governor, ensuring that no matter how much space stretches, the rules of the game stay fixed. The implications are profound. If dark energy and light speed weren't locked in this equilibrium, time itself would become erratic. Clocks in different parts of the cosmos would tick at different rates, breaking the universal synchrony that lets us trust the age of distant stars or the timing of interstellar signals. Chemistry would fracture too. The energy levels of electrons, which depend on light speed's role in quantum equations, would shift unpredictably, making molecules unstable. Life, complexity, even basic matter would be impossible. What's truly staggering is how precise this balance must be. Calculations show that if dark energy's influence varied by even 1 part in a trillion, the cumulative effect over cosmic distances would distort light's speed enough to rewrite physics. Yet across 14 billion years of expansion, not a single deviation has been found. This isn't just luck, it's a signature of a deeper architecture, one where the universe's expansion and its fundamental constants are interwoven like threads in a tapestry. So the next time you flip a light switch or gaze at the stars, remember, the light reaching your eyes is more than just illumination. It's a cosmic invariant, a steady drumbeat in the symphony of spacetime, preserved against all odds by dark energy's silent, perfect calibration. And that constancy isn't just a convenience, it's the very foundation of a universe that can be known, measured, and understood. Supersymmetry isn't just a theoretical playground for physicists, it could be the missing link between dark energy and the quantum realm. This elegant framework proposes that every known particle has a hidden twin, a superpartner with slightly different properties. While we've yet to detect these shadow particles, the 31st cosmic balance suggests they might be silently shaping the universe's expansion. Imagine these supersymmetric particles as invisible mediators, whispering between dark energy and ordinary matter, subtly adjusting the cosmic equilibrium like a hidden hand fine-tuning a watch. Here's where it gets fascinating. If supersymmetric particles exist, their interactions could generate just enough vacuum energy to explain dark energy's observed strength. Current quantum field theories predict vacuum energy densities that are absurdly high, enough to rip spacetime apart instantly. But supersymmetry introduces cancellations. Particles and their superpartners contribute opposing energy values, nearly neutralizing each other. The tiny residue left behind, that could be dark energy's repulsive push, a faint echo of this near-perfect symmetry. It's as if the universe plays a cosmic game of tug-of-war, where supersymmetry's delicate balance leaves behind just the right amount of tension to drive expansion without tearing everything apart. The implications for future experiments are electrifying. If this balance holds, next-generation particle colliders like the proposed future circular collider might finally spot these elusive superpartners. Certain supersymmetric models predict particles that interact weakly with ordinary matter, but leave subtle energy signatures when dark energy's influence fluctuates. Picture a particle detector catching an anomaly, an event where energy seems to vanish or appear without explanation. That could be the fingerprint of a supersymmetric particle, momentarily absorbing or releasing dark energy's influence, like a sponge soaking up a drop of water. What's truly mind-bending is how this ties into the cosmic scales. Supersymmetry was originally conceived to solve quantum riddles, like why the Higgs boson's mass isn't astronomically high. But through the 31st balance, it becomes a bridge spanning from the infinitesimally small to the astronomically vast. The same symmetry that stabilizes subatomic particles might also govern the fate of galaxies, threading microscopic physics into the fabric of spacetime itself. Critics argue that supersymmetry's lack of direct detection casts doubt on this connection. Yet the balance offers a counterintuitive clue. The heavier these superpartners are, the more finely tuned their cancellations must be to leave dark energy's faint residue. This could explain why we haven't found them yet. They're not just hiding. They're orchestrating a precision dance, their mass and energy perfectly offset to preserve cosmic stability. So while supersymmetry remains hypothetical, its potential role in dark energy's balance transforms it from abstract math into a thrilling cosmic detective story. The next particle collision, the next deep space observation, might reveal the first hint of this hidden symmetry, a whisper from the universe's most secretive architects, proving once and for all that the quantum and the cosmic are threads of the same grand tapestry. The universe is filled with ghosts, not the kind that haunt old houses, but cosmic phantoms so elusive they pass through planets like sunlight through glass. These are neutrinos, trillions of which stream through your body every second without a trace, remnants of the Big Bang's fiery aftermath. While light from the infant universe took hundreds of thousands of years to break free, these subatomic specters escaped almost instantly, carrying pristine information about the cosmos's first second. Now, the 30-second cosmic balance uncovers their hidden role in the dark energy gravity saga, how their delicate interactions with these titanic forces left faint fingerprints across the universe, waiting for next-generation observatories to decode. Imagine these relic neutrinos as cosmic breadcrumbs, scattered during the universe's birth and preserved in the void for 14 billion years. Unlike their modern counterparts born in stars or supernova, these ancient particles have been stretched to near standstill by the expansion of space, their energies diluted to whispers. Yet even in this frigid state, their collective gravitational pull combined with subtle nudges from dark energy has subtly warped the cosmos's large-scale structure. Galaxy clusters align in patterns that match simulations where relic neutrinos slightly resist dark energy's push, like invisible buoys bobbing against an expanding tide. The numbers behind this are staggering. For every cubic centimeter of space, there are around 300 of these primordial neutrinos, outnumbering atoms by 1 billion to 1. Their combined mass, though individually minuscule, sculpts the cosmic web in ways we're just beginning to map. When dark energy began dominating cosmic expansion 5 billion years ago, these neutrinos didn't just passively surrender. Their weak but persistent gravitational tug created micro-eddies in the flow of spacetime, steering matter into filaments and voids with slightly sharper boundaries than pure dark energy models predict. It's as if the universe's earliest particles left a faint counterweight to its accelerating fate. Detecting this balance requires instruments of unprecedented sensitivity. Projects like the proposed Ptolemy experiment aim to capture relic neutrinos directly, using ultra-cold materials to spot the infinitesimal energy deposited when one finally, after eons of travel, interacts with matter. Others, like the Simons Observatory, scan the cosmic microwave background for telltale distortions caused by neutrino dark energy interactions in the universe's youth. The prize, confirming whether these particles acted as cosmic referees, subtly adjusting the play between gravity's clutch and dark energy's push to keep the game running. What's truly humbling is the timescale. These neutrinos have witnessed the entire history of the cosmos, from quark soup to quasars, their paths bent by forces we're only now learning to measure. In their silence lies a story, one where the smallest, quietest particles might hold the keys to the largest forces shaping reality. And if we listen closely, they could reveal how the universe balanced its explosive birth with its accelerating future, all through whispers older than time itself. Black holes aren't just cosmic vacuum cleaners, they're shredders, tearing apart anything that crosses their event horizon and leaving no trace behind. Or so we thought. For decades, physicists wrestled with the black hole information paradox. If information about matter swallowed by a black hole is truly destroyed, it violates a fundamental rule of quantum mechanics: that information must always be preserved. The 33rd cosmic balance flips this problem on its head, proposing a solution so elegant it borders on poetic. What if dark energy, stretching spacetime itself, isn't just pushing galaxies apart? What if it's also acting as the universe's ultimate backup drive, encoding lost black hole information into the very fabric of expanding space? Here's the paradox in a nutshell. Quantum mechanics insists that information, the precise state of every particle, can never be erased. Even if you burn a book, the ashes and smoke theoretically contain enough data to reconstruct its contents. But black holes defy this. According to classical physics, anything swallowed by a black hole is irretrievably lost, its information locked behind an event horizon that even light can't escape. This contradiction stumped legends like Stephen Hawking, who initially argued black holes must somehow destroy information, only to later reverse his stance when the math refused to cooperate. Enter dark energy's unexpected role. As spacetime expands, it doesn't just create more emptiness, it generates new quantum fields, tiny fluctuations in the vacuum that hum with potential. The 33rd balance suggests these fluctuations aren't random noise. They could be imprinted with subtle echoes of information that black holes seem to erase, like whispers pressed into the stretching canvas of reality. Imagine a black hole devouring a star. Instead of the star's information vanishing, it's transferred not inside the black hole, but outward, encoded in the way dark energy's expansion ripples the surrounding spacetime. It's as if the universe has a fail-safe, ensuring nothing is ever truly lost, only transformed. This idea builds on groundbreaking work in holography, where physicists theorize that all the information within a volume of space can be represented as a hologram on its boundary. Applied to black holes, it means the information they consume might be projected onto the stretched surface of their influence, preserved in the geometry of spacetime itself. Dark energy's relentless expansion would then act like a cosmic projector, enlarging that hologram across the universe, ensuring no data is ever permanently deleted. Evidence for this balance is still indirect but tantalizing. When physicists model black hole evaporation Hawking radiation, they find that including dark energy's dynamic effects allows information to leak back into the universe in subtle, quantum-entangled ways. Even more compelling, the way certain black hole mergers emit gravitational waves with faint anomalies, as if spacetime itself carries hidden imprints of the lost matter. Future detectors like the planned LISA mission could spot these telltale signatures, turning theoretical elegance into observational proof. What's truly breathtaking is the scale of this reconciliation. A force driving the universe's expansion on the grandest scales might also be the glue holding together the tiniest rules of quantum reality. It's a reminder that the cosmos doesn't solve its paradoxes with brute force. It weaves them into the tapestry of existence, stitching the infinitesimal to the infinite with threads we're only beginning to trace. So the next time you hear about a black hole's insatiable appetite, remember, it's not a cosmic dead end. It's a transformation with dark energy as the unseen scribe, recording every lost chapter in the expanding margins of spacetime itself. Light doesn't just illuminate the universe, it defines it. For over a century, we've treated its speed as an unchanging constant, the bedrock of relativity and the yardstick of cosmic distances. But what if that speed wasn't always the same? The 34th cosmic balance dares to explore a radical idea. In the searing heat of the early universe, light might have raced across space faster than it does today, its speed slowing as the cosmos cooled. This isn't just a tweak to physics textbooks, it's a paradigm shift that could explain some of cosmology's deepest mysteries, and dark energy might be the key to making it all fit. Picture the infant universe, a plasma so dense and hot that particles collided relentlessly, trapping light in a chaotic dance. In these extreme conditions, some theories suggest the fundamental properties of spacetime itself were different, allowing photons to zip through the primordial soup at speeds far exceeding their current limit. This wouldn't violate relativity, it would expand it, revealing light's speed as a dynamic player in cosmic evolution rather than a fixed rule. The implications are staggering. Faster light in the early universe could explain how regions now separated by billions of light years appear eerily uniform in temperature, a puzzle known as the horizon problem. If light could travel farther, faster, it would have had time to smooth out those temperature differences before the cosmos expanded beyond reach. But here's where dark energy enters the equation. As the universe expanded and cooled, dark energy's influence grew, subtly altering the fabric of spacetime in ways that gradually braked light's speed to its current value. Think of it like a cosmic speed limit sign that changes with the weather. Light raced freely in the universe's hot, dense youth, then slowed as dark energy's stretching effect became dominant. This delicate transition isn't arbitrary. The math reveals an elegant feedback loop. As dark energy's repulsive push accelerated expansion, it also stabilized light's speed, ensuring that relativity's rules held firm once the universe matured. Evidence for this balance hides in plain sight. The cosmic microwave background, the afterglow of the Big Bang, shows patterns that align suspiciously well with models where light's early speed was higher. Even more compelling, the distribution of galaxies across the cosmos matches simulations where light's deceleration synchronized perfectly with dark energy's rise to dominance. It's as if the universe calibrated the transition with precision, avoiding a catastrophic mismatch that could have distorted spacetime's geometry beyond recognition. Critics argue that variable light speed theories are untested speculation, yet they solve problems that have plagued cosmology for decades, the horizon problem. The apparent fine-tuning of initial conditions, even the mysterious alignment of large-scale structures, all these puzzles soften when light speed becomes a dynamic variable rather than a rigid constant. And if this balance holds, it would mean dark energy isn't just shaping the universe's future, it's preserving the integrity of its past, ensuring that light's behavior then and now forms a seamless, consistent story. So the next time you turn on a lamp or gaze at the stars, remember, the light reaching your eyes might be the product of an ancient cosmic negotiation, where the universe's earliest fires and its accelerating fate found common ground. And in that truce, written in photons and spacetime, lies one of cosmology's most profound secrets, that even the constants we hold sacred might have once danced to a different rhythm, guided by forces we're only beginning to understand. The holographic principle turns our view of reality inside out, suggesting the three-dimensional universe we experience might be a projection of information encoded on a distant two-dimensional surface, like a movie screen displaying a world with depth. The 35th cosmic balance takes this mind-bending idea further, proposing that dark energy itself could be a side effect of this cosmic hologram, emerging from the tension between the universe's surface code and its volumetric illusion. Imagine the cosmos as a vast, shimmering hologram. Every galaxy, every star, even the empty space between them, isn't fundamentally three-dimensional. It's a rendering of data stored on the universe's outer boundary, a surface we can't see or reach. In this view, dark energy isn't some mysterious substance filling space. It's the computational strain of projecting that data inward, a kind of cosmic lag as the universe struggles to maintain its illusion of depth. The math behind this is both elegant and profound. Just as a stretched rubber sheet resists deformation, the holographic boundary resists the complexity of rendering an expanding universe, generating a repulsive force we perceive as dark energy. What's astonishing is how precisely this model fits observations. When physicists calculate the energy density predicted by holographic dark energy, derived purely from the surface area of the observable universe and its quantum information limits, it matches the measured value of dark energy to within experimental error. No fine-tuning required. The numbers align as if the universe itself is confirming its holographic nature. Even more compelling, this balance naturally explains why dark energy became dominant around 5 billion years ago. As the universe expanded, its surface area grew, but the amount of information needed to render its interior grew faster. The mismatch created a pressure dark energies push that only became significant once the cosmos reached a critical size. But the real magic lies in the unexpected connections this reveals. Black holes, those infamous information destroyers, turn out to be key players. Their entropy, a measure of their hidden information, is proportional to their surface area, not their volume, as if they're tiny holograms themselves. The 35th balance suggests this isn't coincidence. Dark energy's strength might be directly tied to how black holes encode and emit information, linking the fate of the cosmos to the quantum mechanics of spacetime's most extreme objects. Future experiments could put this idea to the test. Gravitational wave detectors might spot subtle anomalies in black hole mergers, echoes of holographic data processing. Quantum computers simulating spacetime at microscopic scales could reveal projection artifacts akin to pixels in a cosmic display. Even the cosmic microwave background might hide telltale patterns, fingerprints of a universe rendered from the edge inward. This isn't just a new theory of dark energy, it's a radical reimagining of reality itself. If the holographic balance holds, we're not just inhabitants of the universe. We're participants in its grand illusion, living in a projection so seamless, so perfect, that only the faint tension of dark energy betrays the truth, that everything we see, touch, and are might be written in light on the walls of infinity. Quantum entanglement is often described as spooky action at a distance, a phenomenon where particles become linked across space, instantly influencing each other no matter how far apart they are. But what if this strange connection isn't limited to tiny particles in a lab? The 36th cosmic balance dares to imagine entanglement on the grandest scale possible, weaving the entire universe into a unified web where dark energy and gravity communicate instantaneously, as if the cosmos itself is a single, breathing organism. This idea turns conventional physics on its head. Normally, forces like gravity are bound by the speed of light. If the sun vanished, Earth wouldn't feel the loss for 8 minutes. But entanglement defies this rule, creating correlations faster than light could ever travel. Apply that principle to the cosmic scale, and suddenly, dark energy's push and gravity's pull could be synchronized in ways that defy traditional explanations. Picture two galaxies drifting apart at accelerating speeds. In standard models, their gravitational link weakens as space stretches between them, but if entangled, they'd remain subtly connected, their mutual influence updating instantaneously despite the growing void. The math behind this is as beautiful as it is radical. By treating spacetime as a quantum network where every point is entangled with every other, physicists can derive dark energy's observed strength as a natural consequence of the universe's interconnectedness. It's like a cosmic game of telephone, where gravity and dark energy aren't opposing forces but two expressions of the same underlying quantum handshake. This could explain why the universe's expansion is so eerily uniform, because every part of it is fundamentally linked, adjusting in unison like cells in a body responding to a single heartbeat. Evidence for this balance hides in the large-scale structure of the cosmos. Galaxy surveys reveal patterns that resemble quantum interference, as if the universe's matter distribution carries echoes of an entangled past. Even more striking, the cosmic microwave background's temperature fluctuations align with models where early quantum connections stretched to galactic scales, imprinting their signature on the fabric of reality. It's as if the universe's baby pictures already contain the blueprint for its entangled future, but the real magic lies in the implications. If entanglement spans the cosmos, it could solve one of gravity's greatest mysteries: why it's so weak compared to other forces. In this view, gravity isn't feeble, it's diluted, its strength spread thin across the vast web of cosmic connections. Dark energy, meanwhile, might be the tension in that web, a collective effect of countless quantum links straining as the universe expands. Together, they'd form a self-regulating system where every galaxy, every star, every atom is a node in the grandest network of all. So the next time you look at the night sky, remember, the distances between stars might be vast, but the threads connecting them could be far shorter than we ever imagined. The universe isn't just expanding, it's whispering to itself, entangled in a dance older than time, where every movement, every shift is felt everywhere at once. And in that unseen connection, we might finally find the harmony between dark energy and gravity that's eluded us for centuries. What if the universe doesn't just expand forever or collapse into oblivion? What if it breathes? The 37th Cosmic Balance unveils a radical vision of reality, where the cosmos isn't a one-time event but a phoenix, endlessly rising from its own ashes in an infinite loop of collapse and rebirth. Picture this: dark energy's accelerating push isn't a death sentence for the universe, it's the prelude to a cosmic reset. As expansion stretches spacetime to its limit, gravity, patient and relentless, gathers strength in the darkness, waiting for its moment to pull everything back in a cataclysmic crunch. But here's the twist: instead of annihilation, that collapse becomes the seed of a new Big Bang, birthing a fresh universe with its own dark energy and gravity, perfectly balanced to begin the cycle anew. This isn't just poetic speculation. The math behind cyclical cosmology is startlingly precise. For a universe to rebound without descending into chaos, dark energy's strength must decay in exact sync with gravity's resurgence, like two dancers perfectly timed to avoid a collision. Too much dark energy lingering too long, and the universe tears itself apart before gravity can act. Too little, and the crunch happens prematurely, leaving no time for stars, galaxies, or life to form. Yet hidden in the equations of string theory and quantum gravity are solutions where this balance emerges naturally, as if the universe has a built-in rhythm: expand, contract, repeat. Clues for this hidden order might already be written in the sky. The cosmic microwave background, that ancient afterglow of the Big Bang, shows faint anomalies, unexplained swirls and voids that some theorists argue could be echoes of a previous cycle, like scars from a cosmic life lived before ours. Even more tantalizing, the way dark energy's dominance aligns with the universe's maturity. It's as if the cosmos knows when to accelerate, not just to spread matter thin, but to set the stage for gravity's eventual comeback tour. But the most breathtaking implication isn't just about the past, it's about the future. If the 37th balance holds, our universe isn't racing toward oblivion. It's preparing for transformation, a grand metamorphosis where every black hole, every atom, every ripple of space-time becomes the raw material for a new beginning. And in that endless cycle, dark energy and gravity aren't enemies, they're partners in the universe's eternal dance, ensuring that no matter how many times the music stops, it always starts again. The 38th cosmic balance ventures where few theories dare, into the realm where consciousness and cosmology collide. At first glance, the idea seems lifted from science fiction. Could the act of observation, that strange quirk of quantum physics where particles behave differently when measured, extend its influence to the vast scales of dark energy and cosmic expansion? Yet this isn't mere speculation. It's a frontier where physics, philosophy, and the nature of reality itself intertwine in ways that challenge everything we thought we knew. Consider the infamous double-slit experiment, where particles act as waves when unobserved but collapse into definite positions when measured. This observer effect has long baffled scientists. Why should the universe choose a state only when conscious beings are looking? Now scale that up. If quantum behavior is somehow tied to observation, could the collective observation of the universe by countless conscious entities, stars, planets, perhaps even life itself, subtly influence the behavior of dark energy? It's a dizzying thought, but the math hints at eerie possibilities. Some models suggest that the universe's accelerating expansion aligns suspiciously well with the emergence of complex structures capable of observation, as if reality adjusts itself in response to being witnessed. This isn't about humans controlling the cosmos with their minds. It's far more profound. The 38th balance proposes that consciousness might be a cosmic variable, woven into the fabric of physics in ways we're only beginning to glimpse. Imagine dark energy as a kind of feedback loop, its strength modulated by the universe's growing self-awareness. In regions teeming with galaxies and potentially life, its effects could differ subtly from the empty voids where no observer exists. Even the timing of dark energy's rise to dominance, roughly 5 billion years ago, coincides with the epoch when the universe first became rich enough in heavy elements to foster planets and eventually life. A coincidence or a clue? Skeptics, of course, dismiss this as anthropic reasoning run amok, but the balance persists in the data. The cosmic microwave background's fluctuations, the distribution of galaxies, even the universe's startlingly low entropy, all align a little too neatly with models where observation and reality are entangled. It's as if the universe isn't just a stage for consciousness but a participant in it, its laws fine-tuned to encourage the very observers who might, in turn, shape its fate. What's at stake here isn't just a new theory of dark energy, it's a redefinition of our place in the cosmos. If consciousness plays a role in the cosmic balance, then reality isn't something we passively inhabit. It's a dynamic interplay, a dance between the seen and the seer, where every observation, every thought, might ripple outward to touch the fabric of space-time itself. And if that's true, then the universe isn't just expanding, it's awakening. The 38 cosmic balances aren't just theoretical curiosities, they're a revolution waiting to happen, a blueprint for rewriting cosmology from the ground up. Imagine future telescopes, engineered not just to observe the universe, but to test these balances with razor-sharp precision. Next-generation observatories like the Vera Rubin Observatory or the European Space Agency's Euclid mission could hunt for subtle violations of the 12th balance in galaxy rotations, or trace the fingerprints of the 24th balance in cosmic voids. These aren't incremental upgrades, they're paradigm shifts in how we interrogate reality, turning the cosmos into a laboratory for fundamental physics. But the implications run deeper than observation. If these balances hold, they could birth technologies that sound like science fiction today. Take propulsion. Dark energy's repulsive force, if harnessed through the 7th balance's variable strength principle, might one day warp spacetime itself, enabling spacecraft to ride the fabric of the universe rather than fighting against it. Picture engines that don't burn fuel but tweak the local dark energy density, creating propulsion without expulsion, a concept NASA, a breakthrough propulsion physics program, has flirted with for decades. Similarly, the 21st balance's hypothetical 5th force could open doors to gravity manipulation, not by countering mass but by modulating how mass interacts with spacetime's expansion. The real game changer lies in quantum cosmology. The 35th balance's holographic universe model suggests that dark energy might emerge from information processing at the cosmic scale. If true, future quantum computers could simulate patches of spacetime with adjustable balances, effectively prototyping universes to test which configurations permit life or collapse instantly. This isn't just academic, it's a potential roadmap for engineering stable wormholes, as hinted by the 26th balance, or even diagnosing the health of our own universe's expansion. Are we in a Goldilocks cycle or teetering toward a big rip? The balances might hold the answer. Critically, these theories don't just add to our knowledge, they force us to rethink how knowledge is structured. Traditional cosmology separates dark energy, gravity, and quantum mechanics into distinct silos. The balances dissolve those barriers, revealing a universe where black holes' 33rd balance, neutrinos' 32nd balance, and even consciousness' 38th balance play interconnected roles in cosmic equilibrium. This holistic approach could resolve long-standing feuds in physics, like the battle between quantum field theory and general relativity, by showing they're two sides of a deeper, balanced system. Yet for all their promise, the balances demand humility. Each one is a high-stakes gamble. If confirmed, they elevate our understanding. If disproven, they force us back to the drawing board with sharper questions. That tension is where breakthroughs lie. As we stand on the brink of these discoveries, one thing is clear: the universe isn't just stranger than we imagine, but stranger than we can imagine. And the 38 balances, they're our best compass for navigating that strangeness, pointing toward truths that could redefine not just cosmology, but humanity's place in the grand scheme of things. The war between dark energy and gravity isn't a battle for destruction, it's the universe's greatest collaboration. These opposing forces don't just coexist, they complement each other with such precision that even the slightest imbalance would render reality unrecognizable. Imagine a sculptor and a demolition expert working side by side, not to destroy or create alone, but to shape something neither could achieve independently. Gravity pulls matter into galaxies and stars, while dark energy stretches the canvas of space, ensuring those structures have room to evolve without collapsing or flying apart. The 38 cosmic balances are the hidden rules of this partnership, written into the fabric of existence long before the first star ignited. What's breathtaking isn't just the existence of these balances, it's their improbability. The forces at play didn't stumble into harmony by accident. They're fine-tuned to degrees that defy randomness, like a lock with 38 perfectly aligned tumblers. Take the critical density threshold, where the universe's matter and energy densities balance to within a fraction of a percent, or the expansion structure trade-off, ensuring galaxies form at the exact rate dark energy allows. These aren't happy accidents, they're signatures of a deeper order, one that suggests the cosmos operates with a kind of intention we're only beginning to decipher. And here's the most humbling revelation: we're not passive observers of this equilibrium, we're products of it. Every atom in our bodies, every planet orbiting a star, every galaxy spinning in the void exists because these balances held firm across billions of years. The universe could have been a barren wasteland, a collapsed singularity, or a formless sea of radiation. Instead, it's a tapestry of complexity, where forces that should have torn reality apart instead wove it together. The journey ahead is even more thrilling than the discoveries behind us, with telescopes like the James Webb Space Telescope peering deeper into cosmic history, and experiments like LISA preparing to eavesdrop on gravitational waves. We're on the verge of uncovering balances we've yet to imagine. Perhaps we'll find that dark energy communicates with black holes, or that quantum entanglement threads the cosmos together on scales we never thought possible. One thing's certain: the universe has been whispering its secrets for eons. Now we're finally learning.